camera if they don't want to. Okay.
Okay, I'll start sharing then.
Not quite yet. Let Chichi get going first.
Yeah,
Okay.
yeah. Just show the schedule first, and then to remind everybody they're being recorded. Should we wait a couple of minutes?
Yeah, where's Manfred?
Yeah, we need Manfred to get going on this first session anyway.
Hmm.
How are you doing, Aude?
I'm very good. How are you?
Good. I'm fine. It's weird. I'm not sure that I'm sharing a proper screen. Can you see the schedule now?
Yes.
We can
Okay.
see the schedule. How
This-
long did
by the
you
way-
use the panel?
The panel is yourself plus these people.
No, how
Yourself,
long?
John
For how
Doyle,
long?
Marco, Dan, and I'm not sure. I know that Dan Lee said he was going to be late because he had a prior meeting.
But
But we're going to start with Ugo's talk.
minutes.
Yeah.
Yeah, we start with a 25-minute talk and then a 25-minute panel.
And then we have a short break before the next thing. Before Eve Marder's talk and then the panel discussion for the neuromodulatory control topic area.
Toby, I'm on.
Good, fantastic.
Yeah, it just.
Okay, Chichi, I guess you
Yeah.
can start. Huh?
Yeah. So I guess we should go ahead and start.
Just a second.
Okay.
I need to arrange my Zoom here a little bit.
Okay.
Yes, I'm ready.
All right, great. Yeah, so welcome everyone to the third day of the workshop. We're going to hear the first lecture from the Learning to Control topic area, followed by a panel discussion. And then the first lecture from the Neuromodulatory Control Group, followed by their panel discussion. And finally, an ethics lecture given by Marcello and Ienca from ETH Zurich. Yeah. And before I continue, I'd like to remind you again that you're being recorded. And so if you don't want to be recorded, then just turn off your video. Okay. All right. And so now I would like to pass pass this over to Toby, who is in charge
No,
of
to Manfred. To
Oh,
Manfred.
to Manfred, sorry, to Manfred. So both Manfred and Toby are leaders of the Learning to Control topic area. So Manfred.
Thank you, Shishi. My name is Manfred Morari. I'm not so familiar to this audience. I think I was a professor at ETH and now a professor at Penn. We're going to have those two sessions like yesterday. First, it's going to be Ugo Rosolia, who is going to give the talk, and then we have a panel discussions in 25 minutes. As a matter of introduction, Ugo did his PhD at Berkeley, worked in autonomous on learning MPC strategies and also autonomous vehicles. And he's now a postdoc working with Aaron Ames at Caltech. Ugo, floor is yours. I should say, if you have questions from the audience, then please enter them into the Slack channel. Thank you.
So, good morning and welcome to this first presentation at the Learning to Control topic area and this Telluride 2021. I'm Ugo Rosolia and I'm a postdoc at Caltech. And today we're going to see how we can leverage historical data to teach an autonomous vehicle how to race. I'm sure that many of you have seen the success of AI on several applications. For instance, we saw the computer program AlphaGo that was able to beat the human champion at the game of Go, the perception system from Waymo that is able to recognize different objects, and several algorithms from OpenAI and Google that are able to perform dexterous manipulation. However, when it comes to very challenging and dynamic tasks, such as running or autonomous driving, the state of the art is still achieved using standard control pipelines. For instance, on the video on the top left, we see Atlas, the biped from Boston Dynamics that is able to do parkour. And on the right, we see Martin, which is an autonomous vehicle from the Stanford Design Lab that is able to drift in very tight environments. And in control, we have a very standard pipeline that can be used to synthesize our control algorithms. And the first step is that we compute an optimal trajectory that we would like our system to follow. And then we use historical data together with our knowledge of the system dynamics to identify a model for the system. And then, given the optimal trajectory that we would like to follow and the system model, we can synthesize our controller using standard control techniques. And so what we can see from this pipeline is that there are several moving pieces. So after seeing the success of AI, there is one question that arises naturally, which is, can we simplify the control design? So let's say that our goal is to design a controller for an autonomous vehicle. How do we minimize the engineering effort? And reinforcement learning comes to mind, as the promise of reinforcement learning is that we can simply collect historical data and use lots of compute power to synthesize a control policy, which is a map from the state of the system to the control action that we can simply send to our actuators. For instance, acceleration and steering in the autonomous vehicle case. And there are several research institutions and companies around the globe which have the mission of synthesizing reinforcement learning agents that are able to learn from the interaction with the environment. For instance, in this video on the top right, we see autonomous reinforcement learning agent that is able to learn how to run in a simulated environment. And we saw several successes on these algorithms on very challenging tasks. However, there is one main drawback. So this is a figure that I took from the paper on the bottom right, where the authors implemented 6 standard model-based and model-free reinforcement learning strategies. And in these 6 figures, we see on the x-axis the data which is needed to achieve the performance reported on the y-axis. And here, the key message is that these strategies are really data hungry. For instance, in order to learn to stabilize a pendulum close to the upright position, it took at least 5,000 data points. And for this reason, applying standard model-free and model-based reinforcement learning strategy on our autonomous racing experiment, if we want to use only experimental data, is challenging. So in today's presentation, we will first review at the very high level the key ideas behind model-based and model-free reinforcement learning strategies. Then we will see a data-efficient framework that can be used in the autonomous racing experiments, and then I will highlight which, in my opinion, are some of the challenges which are ahead of us. And in today's presentation, we're really going to focus on autonomous racing, and we will see how to design the controller that is driving the vehicle in this example. So here we see that lap 1, our controller drives at a very low speed, and after only 10 laps of learning, our controller realizes that it has to cut into the curves to minimize the lap time. And I hope that you can also hear that the tires are squealing, meaning that the controller is really able to operate the vehicle at the very limit of its handling capability. And in order to design this learning algorithm that, again, is able to, is data efficient, we're going to leverage some lessons from the model predictive control community. So let's say that our goal is to compute the steering and acceleration commands for an autonomous vehicle. In a model predictive control framework, we plan an open loop trajectory and over a short time horizon. However, this trajectory is planned over a short time horizon, and our controller might take short-sighted control actions which are too aggressive. For instance, in this example, our controller might plan a trajectory that doesn't slow down before entering the curve. And in order to overcome this issue, we are going to force our controller to plan a trajectory that lands in a safe region from which we know the task can be completed. For instance, in this example, we want to force our controller to plan a trajectory that slows down right before entering the curve. In autonomous racing, we really care about the performance over the entire track. But in this example, we are planning the trajectory over a short horizon. And for this reason, we are going to use a predicted cost, which approximates the tail of the cost beyond our prediction horizon. So for instance, in this example, our predicted cost will encourage the controller to take a sharp turns as the cost is lower when we are closer to the inner road boundary. And in today's presentation, we will see that the prediction model might be identified using historical data, and the safe set and the value function, which represent our safe region and the predicted cost, can also be estimated to simplify the control design. And the prediction model, the value function, and the safe set are three key components used in the reinforcement learning and the control literature. For instance, in model-based RL, or reinforcement learning, we usually want to estimate the prediction model of the system. On the other end, in model-free reinforcement learning, we usually want to learn a value function that maps our current state to the cost. And finally, in safety critical control, we want to compute the areas of the state space where it's safe to operate our system. And in the first part of this talk, I would like to give you a high-level overview of these three topics. So let's start with model-based and model-free reinforcement learning, which have very strong theoretical foundations and have been studied over the past 40 years. And the key idea behind these methodologies is to leverage the principle of optimality. So the principle of optimality tells us that if we want to compute an optimal control action U star, we can solve a minimization problem when we want to minimize cost, where we first minimize our instantaneous cost. So let's say that our goal is to drive our vehicle from our home to the airport while minimizing the fuel consumption. The instantaneous stage cost H, in this example, is the fuel that we are going to consume if we are at state X and we apply our control action U. And in order to act optimally, we also want to take into account the future cost. And this future cost is given by a value function. For instance, in the game of chess, a value function maps all possible configuration of pieces on the board to the cost of, or the probability of winning the game. And this future cost is evaluated at a future state. And so for this reason, we need a prediction model, which is a map from the current state X and the current action U to the future state X plus 1, X plus. And in modern deep reinforcement learning, these two components are simply approximated using deep neural networks. And so what we see is that if we want to use the principle of optimality as stated in this equation, we really need to estimate both a value function and a prediction model. And researchers came up with different strategies, which are model-based and model-free, and allow us to estimate just one of these two components. For instance, in model-based reinforcement learning, we optimize a sequence of control actions, and the objective is to minimize the stage cost over multiple steps, and then we append the future cost that is given by the value function. And what we notice here is that when the prediction horizon is long enough, the effect of the terminal value function can be neglected. So this expression can be simplified as follows. And the optimal sequence of control action can be simply computed minimizing our stage cost over n steps. And the advantage of simplifying our expression as follows is that we need to estimate only our system dynamics. On the other end, in model-free reinforcement learning, we usually define this Q factor, which is given by the summation of the instantaneous cost and the future cost. And this Q factor can be estimated from data. And when this Q factor is known, our optimal action can be computed simply minimizing this Q factor, which is often called the state action value function. So these are the key ideas behind model-based and model-free RL, which were initially thought for systems where we have discrete state and action spaces. And most importantly, for these strategies were thought for problems where our goal is to minimize some cost or to maximize some rewards. However, in safety critical systems such as autonomous driving and drones, we also have constraints. And most importantly, our state and action spaces are continuous. And so, again, when we deal with safety critical systems, the main difference is that we have constraints, and this changes fundamentally our control design. So I would like to show you what are the key challenges that we have to deal when we want to control safety critical system with this drone regulation example. So in this example, we have a drone that can move only along the vertical axis. And our goal is to regulate the system at the same height of a nearby cliff. And in this example, the state of the system is the position and the velocity along the vertical axis. And our input is the acceleration. So we are going to assume that we can command a throttle to the propeller, which is able also to overpower the gravity. And for this reason, the system dynamics are given by a simple linear system, linear discrete time system, where the position of the system at the next time step k+1 is equal to the current position of the system plus the velocity that multiplies some discretization factor. And our acceleration is the control input that can be used to change the velocity at the next time step. And in this example, our goal is to regulate the system at the same height of a nearby cliff. And so our cost can be represented by a quadratic summation of two quadratic functions where we want to regulate our state to 0. And the key feature of this problem is that we have state and input constraints, meaning that we don't want to hit the ceiling or the floor. And most importantly, we have limited actuation. So we cannot apply infinite acceleration or deceleration to the system. And again, in this system, we have that the state is given by the position and the velocity. And for this reason, we can plot a trajectory of the drone on a two-dimensional plane, where on the y-axis, we have the position of the drone along the vertical axis. And on the x-axis, we have the velocity. And our goal is to keep the drone inside this box, meaning that we don't want, again, to hit the ceiling, we don't want to hit the floor, and we have constraints on our velocities. So if our drone is in a positive position and we have a starting negative velocity, then our task is pretty easy, as the drone is going to naturally decrease its position, and we will be able to regulate the system to the origin. However, when the position of our drone is positive and we have also a positive velocity, in this case, we should decelerate our system by saturating our input constraints. And when our velocity is pointing upwards and its magnitude is too high, it might be that there isn't a control action that can keep our system within the state constraints. So in this case, collision with the ceiling is unavoidable. And so here, the key message is that when we have safety critical system, it might be impossible to perform the task for all states which are in the state space. And for this reason, there exists only a subset of the state space from which we are able to complete our task. So in this example, we will be able to regulate the drone to the origin only if we start in the green set. And so with this example, we really see that when we want to design learning algorithms, we want to guarantee that our system never leaves the subset of the state space from which is possible to complete the control task. And designing safe sets is being well studied in the control literature. These sets are also called control invariant or invariant sets. So in the first part of this talk, we have discussed how we can leverage prediction model value function safe set to design controllers. Next, I would like to show you that in order to achieve data efficient learning, we really need to operate at the intersection of these three circles. And we're going to focus on our autonomous racing example, where at each time t, given our position of the car, we're going to predict an open loop trajectory that lands in a safe region and uses a predicted cost to approximate our cost function beyond our prediction horizon. So more formally, at each time t of a lap j, we're going to solve a constrained finite time optimal control problem, where we are going to compute a sequence of control actions u that minimize our instantaneous cost over a prediction horizon n. And here in the autonomous racing problem, the instantaneous cost is 1 if we have not reached the finish line, and 0 if we have reached the finish line. And furthermore, we're going to use a value function to approximate the tail of the cost beyond our prediction horizon. And given our sequence of control actions, we will use a prediction model to compute the state of the system x at each time k. And as we have a safety critical control task, we will enforce that our state of the system belongs to our constraint set. In this case, we simply want to keep our vehicle within the road boundaries. And also we're going to constrain our input u to lie in some set. So we're going to take into account that we can only apply, for instance, limited acceleration. And as we see in the drone example, in order to guarantee safety, we will make sure that our system can always come back to the safe region from which we know it's possible to complete the task. And so next, I would like to show you how we can estimate the system dynamics using historical data. And this is also going to be the topic of this learning to control topic area, where you will learn how to use deep neural networks to estimate the system dynamics. And furthermore, in this topic area, you will also see how to solve this optimization problem where the system dynamics are given by a deep neural network. However, next, I would like to show you a simpler strategy to estimate the system dynamics. So in autonomous racing, our system dynamics are described by a dynamic bicycle model, where the kinematic equation of motion that describe the evolution of the velocity of the position as a function of the velocity are usually known to us, and they do not depend on physical parameters of the system. So we can simply linearize this equation of motions to estimate a prediction model for the system. On the other end, the dynamic equations of motion, those are more tedious to identify as those do depend on physical parameters of the system, for instance, on friction and tire stiffness coefficients. So we're going to use a non-parametric estimation strategy called local linear regression. And so we're going to use this methodology to estimate the system dynamics. And in our experiments, we're going to use the same historical data to estimate the safe set and the value function. However, for time constraints, and also because this is not the topic of this learning to control topic area, I'm going to skip the details, but I'll be happy to discuss them offline if you are interested. And so we use this controller where, again, we learn the safe set, the prediction model, and the value function on our autonomous racing experiment. So here you see the controller at lap 1 of our experiment. This is the California Proving Ground, which is a test track that the MPCA lab at Berkeley shares with Aude in the Mojave Desert in South California. And so here, first, the controller is driving the vehicle on the center line of the road at a very low speed. And then the historical data are used to update our controller. In this experiment, we perform 3 laps of path following. So in this figure, on the x-axis, we have the lap number. On the y-axis, we have the lap time. So we see that we perform 3 laps of path following, and then we use historical data to iteratively update our controller. And so what we notice is that the lap time decreases until we converge to a steady state behavior. And here I want to underline that at any point in time, our control policy is using only 1,000 data points. And the control action is computed using just 100 data points out of these 1,000 data points that we are storing. So in other words, this strategy is extremely data efficient. And this is the closed loop behavior after 14 laps of learning. So here what you can see from the side views is that the controller really saturates our safety constraints and operates the vehicle on the very edge of the racetrack. And also you can hear that also in this video, the tires are squealing at each curve, meaning that the controller is really like saturating the lateral tire forces acting on the vehicle. So it's driving the vehicle at the very limit of handling. And this figure shows the closed loop trajectory from our experiments. So these are experimental data. And here I have color coded the velocity. So we see that when our controller starts, the vehicle accelerates, then we start to brake right before entering the curve, then we accelerate when exiting. And the controller touches the inner apex when entering the curve and the outer apex when exiting the curve. And this behavior is optimal in autonomous racing. And furthermore, here again, we didn't compute a reference trajectory that our controller is tracking, but our learning algorithm is able to explore the state space and find this optimal trajectory. And we saw a similar behavior also on the chicane, which is the most challenging part of our track. So just to summarize what we saw in this presentation, we have discussed which are the 3 key components that are used in the reinforcement learning and control communities. And we saw that in order to achieve data efficient learning, we need to operate at the intersection of these three circles. So what is next? I believe that in the future, we will have to synthesize algorithms that are able to deal with partial observability of the environment. So let's say that our goal is to design a robot that has to find a mag that can be in the kitchen or the living room. We would like to design algorithms that are able to deal with this partial observability of the environment. And furthermore, we will deploy our control algorithms on systems where we have multiple agents that have to interact with each other and where computation are decentralized. And furthermore, when we deploy these strategies on real systems, we often use hierarchical strategies where at different layers, we have different models of the systems, and these layers have to interact within each other. And in order to guarantee safety, we usually assume that the controllers sitting at different layers have different properties. And so the question is, how do we design learning algorithm for which we don't know what the properties of the controller at each layer are? And so with this, I see I'm running out of time, and I would like to thank you for your attention. I would like to mention that the code for implementing the strategy we discussed today is available online, and the topics that I covered today are also discussed in a course that we teach here at Caltech, and the material is available online. So thank you for your attention. I will be happy to take any questions.
Thank you very much, Ugo. How we proceed, or I should say thank you for your very nice presentation, and in particular the very impressive application results on the racetrack. So how I want to proceed is that first I will introduce with a few words the panel. I believe that all the panel members are present. And then I will ask the panel if they have any questions and comments directly to the talk, and later we will then open up for questions from the audience. So let me start with the panel introduction. We have Aude Billard from EPFL in Lausanne, with focus on machine learning, robotics, and computational neuroscience after getting her PhD at the University of Edinburgh. Then my former colleague John Doyle from Caltech, with a wide range of interest and activities, including biology, technology, medicine, ecology, neuroscience, multiple physics, and I could continue for minutes if I had copied all the areas from his website. Then we have Marco Hutter, colleague at ETH, former colleague at ETH. Marco is a professor of mechanical engineering here in Zurich. He's head of the robotics systems laboratory, which is one of 7 labs in the Institute of Robotics and Intelligent Systems. And Marco's focus is on designing and building control technologies for autonomous operation in challenging environments. And then my, again, former colleague, Dan Lee, is a professor of electrical engineering at Cornell Tech and Cornell University. Comes originally from physics, and now he's focusing on understanding computational principles in biological systems and applying that knowledge to build autonomous systems. I think that describes just about the focus of the Telluride workshop. And finally, Terry Stewart, Associate Research Officer at NRC Canada, and I think he's well known to our Telluride participants. And so after that introduction, I want to ask the panel members, first of all, if they have prepared some slides as they were asked to, but even if they, so let me ask, has any one of you 5 panel members prepared some slides? And obviously you're given priority.
Yeah.
Terry,
Yes.
excellent. We were counting on you, if I may say.
Yeah.
Please.
John said yes first, so if he would like to go first.
Sorry, that did not come up here, but I think we'll have time for both. So let's start with Terry.
Right. Yeah, so let me just say, so my work in motor control has been, mostly came out of doing, it came from biological models of trying to understand the, the actual motor system in mammals. But one thing that got pulled out of that was just a very, very, very simple network that we seem to have been able to apply to lots of different situations that is just a neural version of Slotin style adaptive control. For those that don't know what that is, there's this common PID controller approach where normally you just have a little integrator that sits around and says, okay, how much error have I been building up in the past? So that's how much extra force I should be putting on, or extra control signal I should be sending to something. If you just replace that with a neural network with the simplest learning rule possible, like only learning on the output layer, then it turns out that you can use just about any neural network to do that. And we've at least shown some examples where you end up, so for instance, this is learning to deal with either extra forces being applied to a robot arm, so unexpected forces that you haven't modeled, or things like buildup of friction at the joints and things like that. Having the system learn to apply extra forces in different situations. Turns out you can do that really, really cheaply, and we've at least been able to point to that. This is a concrete example that right now, if you try to do that with CPUs and GPUs, it's just way too expensive or is too much latency. And so here's a really, really, really simple learning algorithm you can just apply anywhere that you would do a PID controller. So that's most of the type of motor control that I've had experience with. But I'm really hoping that the sorts of things that are being talked about in this panel, we can go ahead and maybe apply these similar tricks in other situations. Thanks.
Okay, are there any questions directly to Terry? If not, then I take the prerogative of the coordinator here. I'm not familiar in detail with your work, but if all you're doing is replacing the PID controller, then I say, why do I need it? I have mechanical, electrical, and other analogs of PID controllers already.
Oh, sorry, but it's an improved performance over what just an I-term, because you're replacing the I-term with an actual learned function that learns, oh, at different parts of the state space, I should be applying a different amount of extra force. So it's implicitly learning a model of the system. Sorry.
Okay.
Yeah. So it is an improvement over what a PID controller would give you. Yes. Yeah. Thanks.
Thank you. And now I think we have John. At least that's what you said, Toby.
Yeah, John, you have something, yeah?
Yeah, I have just one slide, but I have to.
You can,
Oh, okay,
Please.
there it is. Let me see if I can. Here.
everybody's a Zoom expert now.
Okay, can you see that?
Yes.
Okay. So this is actually a slide I sort of adapted from a recent control group meeting about both the interface between control and AI, but also control in society. So anyway, this is a standard rant of mine. I apologize, but if you've been around Telluride for a while, you've kind of heard this. But in the last couple of years, I think a lot of progress has been made. So I'm going to talk about the elephant in the forest. I would love to get the elephant in the room, or even the room next door. But the idea is that architectures is a phrase that gets thrown around, and poorly defined. But the architectures dominate pretty much all aspects of our lives, from ourselves to our global economics, but sort of lack a theoretical foundation. And what ends up happening is control theory ends up being relegated to filling in boxes that somebody else has designed in a domain-specific way as a largely ad hoc art form. So people who are architects, whether it be buildings or the internet, or practically anything, it's an art form. It's not. It has some engineering in it. But the problem is we have a whole lot of current architectures around us, and they have astonishing systemic fragilities that the last year has highlighted. They aggravate all sorts of things. And can we get ahead of the problems that these are creating instead of just reacting to crashes? So now we put Band-Aids, equivalent of putting Band-Aids on cancer. It looks to me like most trends, including AI, look to make this worse. And maybe not for us, but for the general population. So, and the talent working on this area, which we just saw an example of, is just fantastic. And so my inclination is to avoid working on it just because all my students are, and it seems to, I can't even keep up. So what I can do is say, oh, what could go wrong? And so can we develop a theory of robust architectures that will limit the damage to what happens if we slap layering on top, or higher layer learning? And that's the idea, is that everything we build, we're now going to slap some learning on top of it. And then there's the trade-offs between efficient hardware, because none of our infrastructure is sustainable. We're going to have to make radical changes to the power grid, to water waste, all these things. And all of those changes will make them more fragile. So we're going to have to build complex control systems that give them robustness and flexibility, but those create cybersecurity nightmares. And we don't have an integrated way of thinking about that. And the other thing we need to really do is enable and leverage enormous diversity in the systems instead of suppressing it. And that's this diversity-enabled sweet spots. So I think we've really, and Terry's been huge in helping with this in terms of getting it really focused on neuroscience, but we've been applying it to other areas as well. So there's a bunch of essential concepts. And one of the most important is the distinction between laws, layers, and levels. We tend to, in a murky way, mix those. Obviously, virtualization we're using right now. And there's all sorts of trade-offs. And there's this notion of diversity-enabled sweet spots. That is, why you build an architecture is you don't have any single component that does the job. And then a bunch of other things you may have heard me talk about. But the big thing is locality and sparsity of our reflex layers, and everything saturates. And we just saw a good example of that, where when a system is working well, it's working in saturation. We have to systematically deal with that. So this is sort of a rant. I've got lots of material online, and Terry and I finally got our biking down a mountain paper published in PNAS. That's been taken a long time to get that written in a way that is accessible. And we're now working on another one associated on the muscle side. That was more on sensing side, and one on the muscle side in Fitts law. So, but lots of more details on this issue, and I'm eager to discuss this with everyone. But it's not the heart of what LTC is doing right now. It's kind of like worried about what could go wrong in the future.
So what do you mean by suppressing diversity? Can you just give a simple example for? I mean, does it even appear in this race car or cart pole? Or does it only appear in these large distributed control systems that you're considering here, right?
I've been focusing on large distributed control systems, but I can say what it is in our bodies. So if you look at any part, if you look at the like the cranial nerves, they have incredible diversity. extreme diversity in not how big they are, but in their composition. If you look at the muscles, extreme diversity within the muscles. And most of our theorizing about these problems have suppressed that diversity.
So you're talking about the diversity that you see in natural systems, but is there an example of that in artificial system, like artificial robotic or power grid?
Oh yeah, absolutely. Oh, absolutely. So, so if you look down at the hardware level underneath what we're doing right now.
Okay.
So
yeah.
we're zooming right now, and we're sitting on top of this enormous network that we can effectively ignore because it's all virtualized. But if you do look under the hood,
The internet.
It's not fractal. You don't see a lot of little Zoom meetings going on. What you see is hardware that's incredibly diverse, and we don't see any of that by design. But the point is, we create these diversity-enabled sweet spots. That diversity enables us to create a network that is global, fast, and accurate, even though none of the parts are. Just like our nervous system, we have a fairly fast and accurate sensory motor system, but you go, do we have any parts that are fast and accurate? No. And so you're building, and that's what I mean by it. But there's another thing, which is in society, we tend to do one of two things. We suppress it in one of two ways, either by oppressing the people who are different, or by forcing everybody to be the same. And we have done a poor job of exploiting and leveraging and enabling the diversity that is natural across individuals. But that's way off topic here. This is mostly about big networks, but here's an example in robotics. You could imagine, let's take that PID example. You could imagine doing the PD in passive hardware. So you could do the P part with a spring. You could do the D part with regenerative braking. Why would you do that? To save energy. Now, it may not matter in the lab, but it matters out in the real world. So what you want to be able to do is systematically say, oh, let's replace this part by a spring. What are the consequences of that? Anyway, so that's an example, but it's all over the place.
Thanks a lot, John. And the interest of time, I would like to ask some of the other panel members if they would like to comment on either Ugo's talk, John's comments, Terry's comments. Dan, do you have some reaction?
Sure. Yeah. No, I actually wanted to ask Ugo a question. So, how well does his system perform compared to professional human drivers? Because when you talk to professional, say, rally drivers, they put their cars into amazing things like controlled skids by pushing the brake and the gas pedal at the same time. They do all these sorts of, what we would say are crazy control maneuvers.
Yes. So that's a great question. We didn't compare to we didn't have a true race driver on it, but we have professional drivers which are trained to drive the vehicle at the limits of handling. And we noticed that on the longitudinal component, it would be possible to push the vehicle even more, so braking and accelerating harder. But on the lateral component, we were really at the limit of handling. So we were not as fast as a professional driver, but we were close. So it was faster than a normal driver, also a good driver. And in order to improve the lap time, it would be really important to design low-level controllers. So we were losing performance because we were commanding acceleration, and the vehicle was not able to actuate the acceleration command that was sent from the controller.
But would your model be able to handle things like controlled skids to even go faster around some of those curves, right? To put it into a control.
So I think actually you don't want to skid. So you want to operate the vehicle exactly in the curves, exactly where it's operating right now. So you don't want to drift.
But I thought on more dirt roads, you actually do want to drift. That's what the
Yes, in dirt road, yes, but not in the racetrack that we have. So in the racetrack that we have, a professional driver was operating the vehicle at the limit of handling without drifting. So you really want to hear the tire whistling, because that means that you are operating on the peak. If you're familiar, basically the lateral tire forces as a peak, and then it goes down. So you want to operate the vehicle at the peak of the curves. And in simulation, I've tested that actually that's where we operate the vehicle. So on the lateral components, we are really optimal.
Like in Formula One, you don't see them skidding.
Yeah.
Aude, can I call on you?
Sure. Maybe I'd like to jump back to what John said earlier on. Hello?
And show one of your beautiful robot videos, Aude, please. They're just so lovely. I don't know if you have it available. I just think they're absolutely fantastic, and everybody should see this.
Thanks.
If you
No,
have it.
I
don't want to
did
put you on
not
the
do my
spot here.
duty. I
Yeah.
did not do my job. I did not prepare any slide. My apologies. But I'm happy to share that. So maybe also to Ugo. There are very nice examples also from Asia and Europe that you may want to add in your future slides. You said something, John, that was very interesting. You said that the brain usually is not very fast nor accurate. And I think accurate is extremely important. And maybe that's a criticism that we could make to robotics and optimal control in general, that we're always having an objective function that we're optimizing for. But over the years, I found that it was more important to model the feasibility space as opposed to optimality. And I wanted to throw this to the panel to see how people will react to that, which will also change entirely the way that we actually optimize for the solution that we're looking for.
So what do you mean by that, Aude? I'd like to understand what's the point?
But if I take the liberty, you are entirely right. And if you face any industrial control problem, you're never given an objective function to optimize, never. You're told about all the constraints that you have to satisfy. This is the specification. And so we use the optimization only as a crutch in order to reach feasibility. That's all. But people, the students tend not to make that difference. Let's say that.
It's interesting. So Marco, I'd like to hear to what extent do you think that machine learning can help your animal? I mean, we're going to see the animal anyway on Friday, but that's a heavy duty, multi-degree of freedom platform that has to navigate around in the real world and deal with all kinds of real world constraints. And you must be facing the problem that you're also compute bound, right? You're even compute bound for the control. Is that correct?
So it's heavily depending what kind of controls you're running on it, right? And that maybe also connects a little bit to what Ugo was presenting. So let me share quickly my screen here and connect this to some of the questions that Dan raised before and some of the presentation of Ugo. So the main question that I have here is, why do you think that like the classical control techniques in these types of examples are the ones that have brought this type of, or at this level, the best level that we see in mobility out to today? Is there like a fundamental reason behind that we don't see like classical or standard RL in this, but that we have a model-based control behind it, or what is the main reason for that?
Yeah, that's a fantastic question. And like, I believe that if you look actually the books from Professor Bertsikas, for instance, most of these strategies were initially taught for systems where we have discrete state and action spaces. So if you see like the stunning successes, for instance, like AlphaGo or the game of chess, where you really have this discrete nature of state and action spaces. And so, for instance, something that is not covered by that theory, which is also a question on Slack, is that we don't consider constraints. So in standard reinforcement learning algorithms, so the theory is really thought for system where you want to minimize or maximize something. And if you want to assign, for instance, a cost that is infinity, if you don't satisfy the constraint, the theory actually doesn't go through. And that's why we need to kind of leverage these ideas from control theory, where we model the set of states where the task can be completed. So I think this is what's the main difference is that these strategies were taught for system where the state and action spaces are continuous.
So, and then that connects to what Toby raised in the beginning. So think about the problem like this. So I think we would not even know how exactly we would formulate this as a classical control problem to solve. So this is the type of areas where I think like reinforcement learning is just like getting so much better than anything we see from classical control. And up to today in these complex vehicles like the BDI Atlas or so, we haven't seen this yet, but I think like this is just a question of time until we have all of that. Also in terms of efficiency of all these algorithms, if you run this afterwards, just a trained neural network on the system is just like so much better than anything classical, purely model-based as an optimization problem.
I totally agree, but let me ask you one question. Are these hierarchical strategies where you maybe have learning at a top layer, or do you use these classical algorithms to input torque commands to your robot?
So this is a pure RL learning algorithm that you do in simulation, then you transfer to reality. And to bridge that gap, that's very similar to what you were doing with driving your car, is that you take a learned model and bring that back to your actual system in order to make this discrepancy as little as possible.
You mean you bring it back? Can you just explain what that?
You extend your simulation. So what you were doing is you're learning your tire model, for example, or your full dynamics in that case. What we were doing here is we were learning some of the actuator models and brought that back to the simulator in order to train this control algorithm and then deploy it on the actual system.
So you were learning with the neural network, you were training a neural network with the actuator data and then bringing that back into the simulation.
Exactly, yes.
And decomposing it. Okay, that's what Manfred keeps telling us. We should break up the problem if we want to have any hope.
Exactly.
You know, as beginners.
Yeah.
Aude, what about you? Do you also, you know, you're working a lot with these high degree of freedom robots and imitation learning and things like that. I mean, what is left to do in this area?
I don't know if I'm growing too old, but I feel that we are really not progressing that fast. I'm so sorry to say. I'm not as enthusiastic as Hugo. I mean, maybe because I've been long enough around to see that we are revisiting the same thing. I think what we need is to have true intelligence. I mean, at the minute, neural networks are data storage machine, the same way that they were already when we were discussing them during my thesis, and most people in this room know that. And the true intelligence is not this. Actually, it's being able to reason. It's enormously about reasoning and understanding and interpreting, and we're not anywhere close to that.
Okay.
So I'm sorry. I refuse to be very technical and detailed. I would like to bring this conversation maybe higher up.
It's hard to see how to relate that to the projects that we want to do in the workshop, you know, for the beginners, mostly beginners that will work on these projects. It's hard to define a project that we could actually even explore as a tutorial in this kind of domain.
Yeah, but I mean, you know, imagine that you want to teach this robot driving, and you don't even know what driving is. And so the robot has to reason what's went wrong if it went out of the road and toppled down, you know, upside down and hurt itself. And all it goes is like, ouch. So, and then what about going back and starting to reason what went wrong? When did it go wrong? And I know it's reinforcement learning and it's revisiting all of that, but we're still very far from being able to solve that problem, aren't we?
That's a good point.
Marco?
I had another question to your talk, Hugo. You were talking a lot about Sejnowski and about this max tire force and so on. So can you let us know a little more in detail, like how hard this is actually, you know, to define that on such a system, and how hard do you think that is to do this for a lot more complex system? So do we have hope that you can really define exactly what is safe and what not for such a system? Or do we have to get other techniques in this area?
Yeah, so the key idea beyond defining like what is safe is that if from a part of the state space you were able to complete the task, that's safe. So you can, because you know that like you've been there before and there is a control policy that brings you to the goal. So the idea was simply to train a classifier that tells you, for instance, like some density estimator, or like how many times you've been in a particular part of the state space and you were able to successfully complete the task. So it's not hard.
Okay.
Marco, can I ask you, and maybe you said that before, is your approach to do actually what we have done in design always or forever, mainly decomposing your task into subtasks that you understand and do well, or also decomposing a system design in general into parts that you design well and that you can test well, and then you combine them in order to get the overall behavior? Is that the approach you also resort to, or do you do a whole pipeline approach with your neural net from input to output?
So for this behavior that I showed you before, this is a hierarchy, but only about like one hierarchy is about rolling, one is about standing up, and one is about locomoting. So 3 behaviors, and then a hierarchy that selects which one is the one that is active. But for example, for locomoting across challenging obstacles or whatever, you have one single neural network that takes a complete state or a history of a state as an input and commands joint level commands to it. And on Friday, Juno is giving a lot more details about this and how this works exactly. But there it's really one single network that does that. So the breaking up happens primarily in this modeling aspect. I think we know for many systems, we know very well in how we can model that. But there's certain aspects we have pretty bad understanding from first principles to like do everything to a high accuracy. And I think there it's very important that we break it up, the problem, and have data for certain aspects of your model that you can combine them with the things that you know very well how to model.
And if one of your tasks or parts you find it doesn't work in some complex way in certain situations, what is your approach to fixing this? Is it just saying, I learn more and then it will just get better because I learn more?
It's a bit hard to say in this example. We have other examples where, yes, you have maybe not covered enough data in certain areas of your state space, and there the model doesn't fit well enough based on your data. Then, yes, you go back and you get more data, or you take your experiments from where things did not work that well and you extend your model by that.
Okay, other questions, please.
Anybody have I have a very specific technical question, which has to do with using neural networks to model dynamical systems. And right now, when we do MPC rollouts to do an optimization with our neural network, we have the opportunity with our neural network to represent uncertainty or to represent the distribution, the statistics of probable outcomes. You can't do that typically with an ODE, right? Because ODE is just going to produce a scalar value. You can do it with stochastic differential equations. You can do it with Gaussian processes. But if you have a neural network, you have lots of neurons there, and those neurons can have different opinions about what the answer should be. And that's what you find in the brain in distributional coding. And I'm just wondering if you think that's a promising area to go about. Because if you know how good your answer is, you know whether to trust it or not. Is that important or not to consider? Or is it something that you guys are exploring, like Aude? I don't know if this is something that you even are thinking about.
It's interesting what you're saying, but if you think of the way that we used to model neurons in the brain, these were ODEs, each of them, and they were competing. So in a way, I don't think that mathematically speaking, it's conflictual. What you're raising as a good point is that our system tend to still be deterministic. And if they're stochastic, we still don't know how to bound them properly and to reason about them.
Yeah, I was speaking particularly about this question as one of the things that we pose. There's all these other things that we considered to, these are kind of technical points. Yeah, we were going to ask you, right? But we're out of time, I think, actually.
Yeah, we are, most unfortunately, yes.
Yeah. 3 minutes, but they are interesting questions.
But these are the kind of things that we're going to discuss in the topic area. And I still have a clear memory, Dan, of you bringing your, what was your quadruped and when was that? You had this beautiful dog bot. I can't remember what the name of it was.
Yeah, no, I didn't have a
Remember?
name, but it was a long time ago, and it was great to bring it to Telluride. And I wish we have a chance for everyone to
Should
show
revive it.
in person sometime soon. So.
Okay. I think we should take a little short break now, at least a couple of minutes before the next session starts. Thank you, everybody. Really.
Thank you very much.
Yeah, thank you. Thank you, Manfred, Toby. So
Okay.
yeah, so we're going to take a couple of minutes break, and then the NMC group, neuromodulatory group, will then continue. And Rudolph, there you are. And Scott joining? Or just you, Rudolph?
I'm here too.
I think.
Okay, where's Scott? I don't see him.
I'm here.
Oh, there you are. Okay. Yeah, somehow I'm like lost in some other page of the. Yeah, participant. Okay.
Can you guys let me share my screen?
Yes.
Sure.
Can
Are you
get out
co-host?
that- I'm the speaker.
Oh, co-host. Toby, is she co-host so that she can share her
You
screen?
should be able to share the screen now, Eve. Don't you want to introduce Eve before you start sharing the screen?
It's a break.
Okay.
She just wants to check to make sure.
Oh,
that
I see.
we're-
Okay, yeah. Go ahead. You should be able to share. Yep, it's showing. It's showing.
Okay,
Yeah, it's
so
working.
Yeah, perfect. Now maybe you've got to present. Beautiful
yeah,
slide.
what? Yeah, I want to go from beginning.
Okay.
Okay.
Eve Marder's talking. Look at her art. You want to hear? She works on the.
Still see Shichi will hear you. It's still showing the slide sorter view. It's not showing the presenter.
No,
Have you
it's
started?
not. It's not showing. It's my title slide is what I'm seeing.
No, we're not seeing that. We're seeing your wrong screen. You need to share a different screen, I think, or share the screen instead of the window, because we're still seeing the view with the slides on the side.
Or
What do you? No, I don't think you are. Are you?
No, we are. We're
you
seeing. I'll tell
the
you.
title? You're seeing my slides on the side. So you're seeing. Okay.
Seeing the sorter view. Yeah, you're sharing. You should share the entire screen or share the presenter view.
Eve, I think you have to share your screen and then launch your PowerPoint.
I've never had trouble before.
Or set up PowerPoint so that you only have one screen. You may have two screens.
I only have one screen.
Okay.
Let's try again. Let me just, so I'm in PowerPoint now. I'm going to go from beginning. So I'm just seeing one screen. And now, let's see. Now I'm going to except I can't see anything to share at that point. Okay. So let me try again. So what are you seeing now? You're seeing on the left, you're seeing my slides?
Yes.
Okay, so let me see what happens if I go into slideshow.
Exactly.
From beginning. Now, I don't see the other slides anymore, do you?
But how? It's fine.
This is fine, yes. And can you move to the next slide just to make sure that.
The Zoom quit. What do you see?
We are still seeing your title slide.
It's perfect. It works.
Yeah.
I actually see that Zoom quit unexpectedly.
I think her Zoom client crashed. She has to join the meeting again. It's fragile, especially on some older hardware.
Oh, she may need to install the latest version of Zoom.
It's a great chance to say some words about your topic area right now while Eve is reconnecting.
Unmute Eve.
So you can say a few words about Eve while she's connecting again.
Sure, sure.
Do I have to go all the way out?
So shall we start? Yeah. So welcome everyone. I'm Rodolphe Sepulcre. I'm the co-organizer with Gert Kohenbergs of this topic area on neuromodulatory control. And we very much hope that Eve will be able to come back. Yes, I think she's coming back. I don't think we could hope for a better speaker than Eve Marder to introduce the topic of neuromodulation. She has been, I think, the world leading scientist in that area, and has, through her work, demonstrated the key role of neuromodulation in maintaining the function of nervous systems. And at a personal level, I would say it's really through the work of Eve that I've become convinced that we can regard biophysical neuronal networks as control systems. So we are very excited to listen to your talk, Eve, and without further delay, please start if you can.
Okay, I'm gonna try and share my screen, except you guys we'll see what happens. And now I'm gonna try and go from the beginning. And tell me you see my screen.
Yes, excellent.
Okay, so it's a great pleasure to be here. And I wish I could sit through the whole meeting, but other things have interfered. And what I wanted to do today in this short time allotted is give you a bit of an old and new, starting with some of the new concepts that govern the way we've been thinking about neuromodulation. And I should say I've been studying neuromodulation since the early 1980s. And it's always a challenge to figure out what principles are most important and how much old and how much new to highlight. And I would just like to say that for any of you who want some of the older stuff, about 10 years ago, I recorded for iBio seminars a series of 4 talks. One of them is about neuromodulation. So a lot of the old basic principles are there and they're openly accessible. So I call this neuromodulation degenerate circuits can hide and reveal cryptic individual differences, because what we've been most worrying about in the last 10 years is trying to reconcile individual variability and robustness with concepts of neuromodulation, et And before I like to go on, I'd just like to give credit to the wonderful people who've done the work, past and present. Tim O'Leary is here in this alums, as is Guillaume Drion. And then this is my present lab and all sorts of other truly wonderful people over the years. Now, neuromodulation 2021. Neuromodulation for me means alteration in intrinsic properties of single neurons and synaptic strength. That's the basic vocabulary of what neuromodulators do. And today I would say neuromodulation acts as a source of behaviorally relevant plasticity by changing circuit dynamics. And this is the feature we focused on in the first 20 years of neuromodulation, or maybe the first 30 years. But today we also are really interested in how neuromodulation can contribute to circuit stability by compensating for cryptic variability in circuit components. That is to say, neuromodulation can act to hide a lot of animal-to-animal variability or to compensate for it. And I think this is the problem that I find most fascinating in today's world. Now, just to start at the beginning, the preparation that I'm going to be using is the crustacean stomatogastric ganglion. The stomatogastric ganglion, which you see on the left, consists in crabs about 25 or 26 neurons and lobsters about 30 neurons. And the way we do the preparation is we take the stomatogastric nervous system outside of the animal. These are lobsters and crabs. Most of the data I'll show you are from crabs. We get them from the local waters via fishermen and fish distributors. And then we take the stomach out of the animal and we dissect the nervous system from the surface of the stomach and put it in an in vitro Silgard line Petri dish that allows us to have complete accessibility to the nervous system. The stomatogastric ganglion, as I said, is at the center. We can record intracellularly. And here you see intracellular recordings that allow you to see fluctuations in membrane potential as a function of time. or extracellularly, that allows us to see action potentials over time in any of the constituent neurons. Now, the pyloric rhythm, which is the first part of this, is a triphasic motor pattern, which is LP, PY, PD. It repeats throughout the lifetime of the animal, and it is probably one of the best understood rhythmic motor patterns that's known in neuroscience. And if you want to think about it, you can think about it as sort of similar in some ways to your respiratory rhythm. It's always on, and it's always generating a series of bursting and rhythmic motor discharges. And what you see here is in the red, you see the extracellular recording on a mixed nerve has all of these units. And so you see LP, PY, PD, LP, PY, PD. And here is the connectivity diagram, or the connectome that was established by 1980. So we go way back. And what you see, and I'm going to tell you quickly how it works. We have a bursting pacemaker neuron called the AB neuron, which is electrically coupled to two PD neurons. This is a pacemaker kernel. All of these filled symbols are inhibitory synaptic connections. So you see here a lot of what we call half-center oscillators, reciprocal inhibition, PD and LP, or LP and PY. And the way the network generates the rhythm is the pacemaker kernel rhythmically inhibits both LP and PY. LP recovers from the inhibition before PY, so it comes up, and then it holds down the PYs. Eventually the PYs recover from their inhibition, turn off the LP, and then the whole thing starts over again. Can somebody turn off their microphone? Yeah, thank you. So this is what you see when we leave descending modulatory inputs intact, and we see this lovely rhythm. And I'll show you in a bit what happens when we take those modulatory inputs away. But before that, I want to show you what the real stomatic gastric nervous system is doing. There's another rhythm produced by the stomatic gastric nervous system, and this is called the gastric mill rhythm. At the time scale of these recordings, and this is probably 15 seconds, the pyloric rhythm, that triphasic rhythm, is seen up here. It's the fast rhythm. You also see a much slower rhythm. This is the gastric mill rhythm. And this moves some teeth inside the stomach. And notice in this smaller rhythm, you have alternation between this neuron called LG and a neuron called DG. And you have alternation between the LG and an envelope of activity in these two other neurons, which are actually firing in time with the pyloric rhythm, and they're also firing in an envelope of activity in time with the gastric mill rhythm. So these neurons are part of two different rhythms at two different time scales, and then we have the slow rhythm here. Now, unlike the pyloric rhythm, which is pacemaker driven, this rhythm comes about, the gastric mill rhythm, by totally different mechanisms. And what I think is really interesting for those of you who are thinking about controlling networks is what I'm going to show you in the next slide. This is a little bit complicated, but I just want you to get a sense of where we are. This is work that Mike Nussbaum is largely doing. So this is a diagram of the stomatic gastric nervous system, and it shows some modulatory descending neurons. One of them is called this neuron MCN1. When you fire this neuron, it turns on a gastric mill rhythm. You can also turn on the gastric mill rhythm by applying modulators in the bath. And here you see two examples. Here's an MCN1 rhythm with alternation between LG and DG. And here you see a peptide in the bath producing alternation between LG and DG. Now, by many, many criteria, and protraction and retraction shown here, these two rhythms look almost identical. However, we understand the circuitry and the connectivity by which they arise, and these rhythms, which look very similar, arise by very different circuit mechanisms. So these are degenerate circuit mechanisms. And I'd just like to show you a cartoon with what we've been doing. So we were interested to see whether these two rhythms that arise by degenerate circuit mechanisms, what happens when you perturb them? And so we perturb them in two ways. One, by adding another hormone to the two kinds of rhythms, or by activating a sensory neuron. And so in one case, the hormone, the same hormone on the two different rhythms that were started out identical, but it separates them. And that's because the hormone acts on via exactly the same membrane receptors in the two cases, but it produces two very different outputs. However, a sensory neuron, which has a very complicated series of connections, actually acts on the two different kinds of rhythms and gives you a very similar set of results. So you can have different circuit responses activated by the same mechanism and similar circuit responses by different mechanisms. And I think this is sort of an example of the richness of neuromodulatory control pathways and how challenging it can be to infer mechanism without really being able to go in and do manipulations, etc. So these are some of the kinds of problems we're studying now. Now, neuromodulators, and this is for anybody who wants to understand neuromodulation in real brains. This is what we know in 2020 about 2021 about modulators in the sympathetic nervous system. The neuropill here is shown receiving, there are 25 sets of descending modulatory neurons. I showed you a couple of those before that release a ton of substances. These are all neuropeptides, all the amines that you would know about. And then there are also a ton of hormones that are released by neurosecretory structures, including the pericardial organ outside of the heart. So this is a system which is the salient point, and I think it's really, really important for those who want to think about neuromodulation. One nervous system is modulated not by one, not by two, but by many different neuromodulatory substances, and they can be found in both descending or activating specific pathways, and they can be hormonally liberated. And so the challenge of really untangling all these problems about neuromodulation can be quite daunting, but I think it's that richness that you want to keep in your mind and not ever fall into the trap, what I consider the big trap of saying neuromodulation equals the action of dopamine on X. It's never dopamine by itself. It's never acetylcholine by itself. It is always multiple modulators acting in concert. Okay, now just a few other global statements. Here's the connectivity for the full pyloric rhythm in lobsters. We now know that each neuron has multiple currents subject to modulation by many substances, and each synapse is subject to modulation by one or more substances. Now, if you think of a connectivity diagram or a circuit diagram or a control pathway, and you imagine that every single component is subject to modulation, you should be really worried, because you could say, well, how does it maintain its fundamental integrity? And I would like to say that this network continues to work extraordinarily well despite this extensive neuromodulation, and we only incompletely understand where the stability rules are so that the network integrity is not completely destroyed always by neuromodulation. We can come back to that in the discussion. Now, but I just want to show you now, switching gears a tiny bit, these are extracellular recordings of the pyloric rhythm that Adriana Topolik created just for this slide. So she's just recording the pyloric rhythm from 5 animals, and you can see here the raw traces, and you can see how similar they are. Yeah, they are a little bit different in frequency, but they all show that characteristic LPPYPD, LPPYPD behavior. And when she recorded intracellularly, you can see some of the waveforms, animal 1, animal 2, animal 3. You can see these 3 animals are virtually identical in their intracellular waveforms. But remember, and this is in the presence of modulatory inputs, but the complication is that when we look at either the currents that we measure using voltage clamp or the gene expression for a ton of different ion channels, what we see is the mRNA copy number varies. And this is all data from single PD neurons. These vary usually 2 to 6, 2 to 7-fold. And you can see here, there's a range. And there are some very important correlations in the expression of many of these genes. And those correlations probably arise during development and may be important for settling into the parts of parameter space in which this network works. But here we have another conundrum. You see very stable across animal behavior. And yet, when we look across animals, we see very large fluctuations in parameters. Now, the story gets a little bit more complicated or more interesting if we remove the descending modulation from the network. So these are experiments that we have been doing in one way or another since the early 80s, or actually since the early 70s. But this happens to be a study that Al Hamoud did a number of years ago. What he's doing is he's first showing you the control rhythm. That's what you saw before, LPPYPD, perfectly lovely. And what he's showing you down here is there were 123 animals that went into this data set that have differences in their frequency, but they show pretty constant, and this is an old finding again, pretty constant phase relationships. That is to say, the normalized time that each element fires in that triphasic rhythm is maintained across frequency. However, when he removes those descending modulatory inputs by cutting or blocking this nerve, thus removing all those inputs, the frequency slows way, way down, and you can see that here. And you can see that in this histogram. The whole histogram moves to the left. But what's interesting is we lose the constant phase, and now we have a constant latency. So the whole network has changed, and that's because we now have these really long delays as you go slower than about 0.7 hertz. So what this is telling you is that some part of this appropriate set of phase relationships depends on the existence of these modulatory inputs. Now, and they're quite variable in the absence. I just didn't show you that. Now, I'm going to take advantage of that to use a perturbation. This is a perturbation that we've been studying for the last 10 years, which is changes in temperature. These animals live in the ocean. The ocean changes temperature, and I can tell you it has changed in temperature a great deal in the last month because I've been swimming in it, and it's gotten quite warm, and crabs and lobsters live in waters that can go from 2 or 3 degrees centigrade to about 25, and hopefully not hotter than that this summer, although it doesn't look good. And so the question is, what happens when all of the ion channels and receptors and all the intracellular machinery, which is all influenced by temperature, what happens to the robustness and the reliability of the rhythms as a function of temperature? I'm not going to show you a series of studies on the intact nervous system with the modulators left intact, but I'd just like to say that between temperatures up to about 25 or 26 degrees, the rhythms maintain their triphasic motor patterns totally beautifully as a function as the temperatures increase. And only when you get to very extreme temperatures do you get what we call crashes or breakdowns. So these are now experiments that Sarah Haddad did, and she wanted to say what would happen to the reliability of the rhythms in response to temperature perturbations in the absence of modulators. So she's showing you here 3 animals, animal 1, animal 2, animal 3. And at 11 degrees, these animals had a very different starting pyloric rhythm. This one looks pretty good. This one looks pretty good. This one looks pretty raunchy. And then she increases the temperature. This one maintains a good triphasic rhythm all the way up to 31 degrees, 27 degrees. This one did fine up to about 23 degrees. And this one started out lousy and got increasingly poor. So you can see a very great diversity, more diversity in the modulator removed rhythms than there were when the modulator was present, which you saw in Adrian's slides. And now she's going to look at the effects of modulators. And to do that, what she's going to do is, as the rhythms fall to pieces, she's just going to score them in terms of the kind of behaviors that you see. And so she's just created categories of good rhythms and silent rhythms and less good rhythms. And we're just going to use these color codes to show you what happens. And in all of her slides, the normal rhythms were this dark purple and this light yellow, and you'll see those again. And so then here's what you see in those three preparations I showed you before. This one started out slow and triphasic and went fast and triphasic. This one started slow triphasic and again went faster. And then eventually at high temperatures, it started showing all sorts of other different kinds of behaviors. This one started out not triphasic and then became triphasic at high temperatures and short stretches. And so you can see how different those three are from each other. And now we're going to look, she's going to look at the effects of modulators on network stability and response. And so the question is, will a modulator make things better or worse in terms of stabilizing the rhythms as a function of temperature? Okay, and we're going to look at two modulators here, proctolin and oxytremerin. This is a muscarinic-cholinergic agonist. This is a neuropeptide found in arthropods, and serotonin. Serotonin acts on a number of different currents, and these two act in a very similar way on an interesting increase in inward current. Okay, so here are two animals in oxytremerin, animal 1 and animal 5, or animal 4 and animal 5. They both started out pretty well, and they maintained good rhythms all the way to 31 degrees. Here's proctolin, animal 6, animal 7. Notice how different they were in proctolin at 11 degrees. These guys were doing very well at 11 degrees. Oxytremerin actually has been long known to produce stable pyloric rhythms at 11 degrees. These two are very different at 11 degrees, but notice they maintain their triphasic patterns throughout the temperature regime. And you can see that here, normal, there was a little gastric activity present in this one. And this was a slow normal, slow normal, fast normal. So you can see that these two modulators, in a sense, stabilize the rhythm. However, serotonin, if we just look at what happens in serotonin, neuron 8, neuron preparation 8, 9, 10, 11, oh, this should be 12, started out in serotonin looking very, very different. And now as we look at the effective temperature, you can see they all are producing not a great rhythm. And you can see that here in the behaviors. You can see a little bit of that purple here, a little bit of purple here. Every now and then you see some good purple behavior, but you can see there are tons of different transitions and irregularities in the rhythms. And so the conclusions that we got from these crashes, at low temperatures, all networks are well behaved with the modulators present, showing consistent changes in frequency and outstanding temperature compensation. I didn't show you this, but each animal seems to crash with individual dynamics because they have underlying parameter differences. And here, some modulators may expand the stable range of temperatures. That is to say, they're hiding some of the variability that is present without them, while others make the preparations more temperature sensitive. Now, I think I have a couple more minutes. I just want to show you one more slide, which isn't directly neuromodulation, but I think is relevant to thinking about how real neurons work. So this is a model neuron with 8 currents, an inward sodium current, 2 calcium currents, a hyperpolarization activated inward current, 3 potassium currents, a delayed rectifier, calcium activated K, and an 8 current. So this is a canonical sort of semi-simple real conducted space neuron model we're going to be using. And Leandro Alonso, who just made these slides, is showing you here a bursting neuron, which you can think of as a model of the ABPD cells. And now he has a way of visualizing what's going on with all the currents. And so in voltage clamp experiments, we always display outward currents, that is to say the currents that would inhibit the cell going up and inward currents going down. The total outward current here on a log scale is shown here. The total inward current is shown down here. And so now we can see in purple, that's the contribution to the total outward current of the A current. That's one of the K currents. In orange, another one of the K currents. That's the calcium activated K. And then in yellow, the third major potassium current. So using that method of visualization, now I can show you something that you probably all realize, that it's very easy to get very similar behavior using very different sets of parameters. So here we have 6 models. Model 1, whoops. Model 1, Model 2, Model 3, Model 4, Model 5, Model 6. They have very similar behavior, but here in purple, the A current is very small in Model A, and it's very large in Model F. And you can see the orange is very different here than it is here, etc. So these sets of conductances and these sets of conductances can produce very similar behavior, but and the currents actually do not necessarily reflect what the maximal conductance was, but this is just another version of what we always call multiple solutions or degenerate pathways. And I'm just showing you this to make one more point, which I think is really relevant to people who think about building devices. So what Leandro did is he took this model, the same one you've been looking at in the previous slide, and he took it through swings of temperature in the model from 10 degrees to 25 degrees. And now he's plotting just the last spike in the burst. And he's plotting it using his current scapes. So here there's a really large contribution of the A current. Here there's a very small contribution of the A current. Here there's a very large contribution of the delayed rectifier. It's another K current, small, and the orange one is getting larger and larger as you go higher. So I love this slide because it makes a point that is very, very, very salient, which is in biological systems, I think, use multiple currents to smoothly change through mechanism. Because they have multiple currents with overlapping voltage and time dependencies, they can actually respond to perturbations by smoothly moving through mechanisms rather than getting caught in sort of small areas of defined by limited areas of parameter space. So this is what the richness of biology can give you. And I like to say that I'm pretty sure that the reason why real biological neurons have so many different kinds of channels in them, although you don't need them for any one particular set of dynamics, is so that these neurons can smoothly move through different dynamical states. And I will stop there and thank you for your, just end on this last question, which is what the neuromodulatory conundrum: how can circuits be reliably modulated without running the risk of overmodulation, and then where are the stability rules? And I have many ideas about this, but I'm sure there are many things we don't yet understand. And I'll stop there.
Thank you very much, Eve. I think we are going to move directly to the panel discussion, and questions to Eve's talk can be asked during the panel discussion, if that's okay. So I will give the floor to Tim O'Leary, who will moderate the panel discussion. So Tim, if you want to, yeah.
Okay, thank you, Rodolphe. Can you hear me okay?
Good.
Can you hear me okay?
Yes.
Yes.
Great. Okay. Well, thanks for this opportunity. I just want to say that this workshop is really fascinating and exciting, and something which brings together biologists and engineers in a way that I wish we saw happen more often. So on this panel discussion, which I'll moderate, we have Eve, who we've just heard speak. We also have Todd Coleman, professor at Stanford, a bioengineer with a sort of intimidating range of contributions, from work on gastric motor activity all the way through to statistical inference and information theory. Terry Sejnowski, who doesn't really need an introduction, he's a sort of a founding figure in theoretical neuroscience and in this workshop. Guillaume Drion, a colleague of mine, University of Liège, again, a polymath, someone with a background in medicine and in engineering. And in my humble opinion, understands conductance-based models better than anyone else in the world. John Doyle, who again needs very little introduction, and a control engineer who has made major contributions to robust control, as well as really interesting and deep work on understanding biological complexity. So there's been a number of questions that have been forwarded to me for discussion on this panel. I understand the panelists will have things they want to contribute. In looking at these questions, I felt it was helpful, at least for me, to have a picture in my head about what we mean when we talk about neuromodulation. And Eve apologized for not including the old stuff in her talk. So I'm going to put one slide in which has some old stuff in it, which includes some of Eve's data and some of Terry's, that sort of sets the scene for what, you know, modulation is. And we could think of things this way, think about what the actual control action of neuromodulation is. And as Eve said, neuromodulation switches cellular properties. Here's a beautiful example of this. So here's a cell in the STG, which is in control conditions, and you pass current into it and it spikes, much like any artificial neuron would or any model of a neuron would. Then bath apply a peptide, and suddenly now this cell becomes bistable. Now, I would take this to the theoretical neuroscience community or an engineering community and say to them that you can tie yourself in knots trying to get a network to exhibit multi-stable behavior and exhibit this type of short-term memory. When you look at what the biology does, it doesn't do that. If it needs multi-stable or bistable behavior at a particular point in the network, then the cellular system that needs that behavior ends up exhibiting it, and it can be turned off and turned off. So here we have an example of a cellular short-term memory that's robustly implemented and is turned on and off with a neuromodulator. And this theme of neuromodulation, turning things on, turning things off, applies at the network level. So again, here's data from Eve's lab showing the variety of rhythmic patterns that you can get in a reduced preparation from the STG by applying these different types of modulators. And you could think of these things as switches on a box that can select different programs somehow. And this goes all the way to behavior at the sort of the global level of an animal. This is classic work, sort of disentangling the different type of rhythmic behaviors you get in cortical and thalamic neurons, which essentially partition into two very different sort of rhythmic behaviors that are in part controlled by the action of neuromodulators in these different parts of the brain. So there's abundant evidence that neuromodulation does control behavioral states. So what we see here is really this idea that a neural system switches between different regimes under the action of these different chemical signals. And this happens at multiple different levels. It happens at the sort of single cell level all the way up to the brain level. And these are mechanisms that, to my knowledge, we just don't exploit or attempt to exploit in neuromorphic systems to date. So the questions that we've been given are, what is the role of neuromodulation in regulating neural function? And that to me is certainly a very broad question. Which neuromodulation mechanisms support robustness of computation under both internal and external variability, which is a theme that Eve's talk touched on extensively? Is neuromodulation control essential to enable robust operation of neuromorphic systems interacting with an uncertain environment? I take that question to mean, should we try and emulate neuromodulation in neuromorphic systems? Is there something essential to it? And how can such systems attain a high degree of reliability, precision, and agility at the system level, at the emergent level, despite operating with biological machinery, the neurons and synapses that at the individual component level are intrinsically unreliably precise and sluggish? I think that's an interesting question, possibly controversial. I hope people have things to say about it. And here's one of mine. How would you actually design a neuromodulator control system from first principles? So those are the questions, and I'll now open to the floor or to the panel. And in particular, if there are questions directly related to Eve's talk, we could perhaps address those first.
So could I address one of those questions and Eve's at the same time?
Sure.
So you brought this slide up from, that was actually a review paper in Science. It's been cited like 2,000 times because it got to the core of that issue, which is that neuromodulators basically can reconfigure during sleep, not just intrinsic properties, but also global properties. And when I give a talk, there's, the thalamic cells are called relay cells when you're awake, but when you fall asleep, because of the fact that there are new currents that are unveiled because of the neuromodulatory changes in the level of neuromodulation, you get bursting. And in fact, sleep spindles occur, thalamocortical sleep spindles. And what I like to tell the audience is that when you fall asleep, a lobster awakens in your thalamus, which I think is attributes to the fact that we still have these very same mechanisms in our brain that Eve has uncovered. But I want to address the issue of should we emulate, and this is a really a field that is really moving very quickly, because now that we have an AI that is based on similar framework or principles, multiple very large number of individual units that are communicating very densely. And now, looking at changes in the strengths of the synapses, learning, that has opened a bridge for the first time in AI between, advances in the neuroscience side that may actually help produce better engineering devices, and vice versa, as we create better, solutions to problems, engineering problems. That actually has been a tremendous source of inspiration to a lot of people in neuroscience. So I think this is a really important bridge. And the one issue that I want to raise, which is the one I'm going to talk about, I think next week, is the fact that it's possible with neuromodulators to actually shift in the very same network, right? We start with the same, Eve starts with the very same 30 neuron network, and the neuromodulators are able to uncover different subsets which produce different behaviors, the two different rhythms, and pyloric and gastric. But that's an incredibly, and I've read sleep, but is another good example of that. And that's something we don't see in most of these deep learning systems, that you train a network to do one thing and that's it. But what I'm going to show is that, in fact, by using neuromodulators during the learning process, you can get the very same network to be able to do many different tasks. You can shift gradually between these different tasks. So I think that's an important principle that we'll hear about. But now a question to Eve. Okay, so you showed there that you have all these different neuromodulators, and that when you bath apply them, you can see shifts occurring both in the properties of the neurons, but also in their global behavior. That's kind of a hormonal type of interaction, right? You bath apply it. The question is, what's the degree of specificity of the individual inputs coming from above? A single neuromodulator it's not a hormonal system. It's affecting certain neurons. And what's the degree of specificity? Have you been able to understand that? And the reason I bring it up is that we don't know the degree of specificity in mammalian neuromodulatory systems. That is to say, we know that, say, the dopamine neurons that we've mentioned, they project very broadly throughout the entire cortical mantle. But the question is, for a single neuron, does it have a specific region or area? My guess is that it does, but Eve probably has more.
So yes, I took out the slides that showed there are 3 different neurons that contain this neuropeptide proptylin. Proptylin is both found hormonally and it's found in terminals of 3 different descending modulatory neurons. It's found with different co-transmitters in each of those cells, and each of those cells has different effects on the pyloric and gastric mill. So the proptylin that's released from the terminals of these cells actually doesn't reach everybody, and it reaches different fractions of the neuropil with different co-transmitters. So by packaging the same peptide with different co-transmitters, and by looking at where receptors are, et cetera, you can use the same modulator in 3 very different neuromodulatory pathways. And we find that over and over again. Now, the fact that the same substances are used both hormonally and in some of these descending pathways is also important, because the hormonal levels probably set a low neuromodulatory tone. And then, so the hormones often act at very low concentrations, and they may set a neuromodulatory tone. And Deb Barrow spent a lot of time worrying about this. And then the descending ones come in and can be acting at 5 orders of magnitude higher concentrations, and then can work differently.
So I think one of the lessons we learned from this, Eve, is that biology has incredibly precise mechanisms, and it can be very highly targeted, way beyond what you see in the textbooks. You know, when you read in the textbooks, it's kind of everything is kind of made very broad, that you know that these neuromodulators just, you know, they're like the very widely diffusely distributed. But my guess is you're right that this is probably, if it's true in the lobster, it's almost certainly true in the mammal
and in humans
and in us, right?
Don't forget humans.
Can I just add a follow-up question to that, though, Eve? So the other thing you mentioned with where you showed the experiments from Mike Nussbaum's lab is that even if you do bath apply analogous neuromodulators, somehow the network makes sense of that signal and drops into it. It gracefully responds to these somewhat off-target signals. So even though you might have very precise targeting in the intact system, it seems like in many situations you can achieve similar changes in behavior, and you know, this is the basis of pharmacology, right? Even when the targeting is not so precise,
right? Because in the case of those 2 networks, which the 2 motor patterns which look very similar, because they were evoked by different circuit mechanisms, the parameters that are there that the modulator now is going to act on, it's going to find either the same or a completely different response.
It seems like that's a clue as to how because I think that the mystery for me here is how this gets set up in the first place so that it works. And the very fact that there seem to be these wide open parameter spaces where you can move between analogous states using analogous signals, you know, there's a certain robustness in all of that. You can be fairly sloppy about what the modulatory signal is sometimes and the resulting parameter space. And it seems to suggest that the network is tuned to find safe regions.
I think these networks are tuned to find safe. And I would say that half or 2/3 of the modulatory actions are actually there to find safe while allowing plasticity. So, I mean, and this is the thing. If you look at all the modulators, you know, many of them activate a pyloric rhythm. If you remove all the modulators and you lose the pyloric rhythm, you can reactivate a perfectly good pyloric rhythm with many different modulators. And so it's almost as if they're there for insurance. And I think, you know, yes, they're all plasticity mechanisms. They all can produce reconfigurations that can do slightly different motor patterns. But you know, depending on what you look, do you have a triphasic rhythm, yes or no? You can get there by a ton of different mechanisms. And then are those triphasic rhythms slightly different? at that point, you'll get slightly different ones with each modulator.
So how do the neuromorphs respond to this then? So people like Gert, and I guess Guillaume sits in the middle, and Rodolphe certainly.
Yes, and I would like to address some of the questions here at the bottom of the list, which is actually very important for this workshop, right? So how, since neuromorphic engineering hasn't really embraced neuromodulation, at least not fully. I mean, we have heard of dopamine modulation, right? But mechanisms of neuromodulation for getting at the robustness of those circuits should be more explored. And so the question I'd like to raise here or ask to the panel, for the participants, right? So what lessons can we learn from all this, right? In configuring, let's say we have a system here for the workshop, right? With Neurodin, which has, neurocube. So we have 16 neurons coupled to synapses, chemical synapses, electrical junctions. And then we have actually 1,500 parameters, digitally controlled parameters, right? Some of which can be thought of as neuromodulators, right? So we have this vast complexity here, right? And so clearly, if you have so many parameters, you should be able to get at almost any behavior that you want, right? But how can you make this robust against all the variations in the analog hardware? And so what takeaway lessons can we take here, right? From the biology and from control system perspectives that can handle this vast complexity and give this reliable, simple patterns of dynamical, behavior that are robust under all these different environmental and also internal noise variability and problems.
Does a clue to that lie in the architecture? So in the last session, John Doyle was vehemently defending the idea that we should look at architectures of these things, not just the components. So the STG, and Eve will shoot me down here, the STG is not an arbitrary pattern generator. It's good at certain patterns. And it's kind of hard to knock it out of those patterns. And there's something about this, the connectivity of the circuits and the properties of the cells that makes sense, perhaps for generating a triphasic rhythm. So that's probably part of the consideration, right? So when you're trying to make an artificial CPG, you sort of think, well, maybe we should wire it up in a certain way and then deal with the rest of the uncertainty in a different way.
So I can just speak for John. Maybe I hope I can speak for John if he's still here.
I'm still here.
Oh, good. Okay. Well, we have this paper in PNAS.
I'll correct you after you speak. Sorry.
I'm counting on that, John. But no. See, I think one of the problems is that this is true of computational neuroscience as well as a lot of other areas, is that we've been focusing on neural circuits, single circuit. But the real problem in the brain is how you put together all these circuits into a globally organized system. And as John points out, it's a layered system. And in engineering, we don't have a theory for that. Although John does, he'll tell you what his theory is. But that's a different level of architecture that we are just beginning to explore. And I think the key, and John mentioned this in his panel, is diversity. And that's what you see it all over biology. I mean, it's not just in the sizes of the axons or individual variability between individual neurons. No two neurons are exactly the same. But that has not been incorporated into these engineered deep learning networks. And I think, again, and that has to be important for being able to deal with the problem of robustness, right? We see that in the lobster, and again, I think that we're going to see that again in mammalian circuits.
So let me just chime in a little bit on this, because I do think that these are great questions for setting up this issue of layered architectures, because we want to build systems that both have flexibility to do a whole bunch of different things, but do each one of them fairly robustly. And so let me just quickly describe a system that we know exactly how this is done. So let's just think of our laptops or the internet or any of our computers. At the very bottom level, the transistors in CMOS digital VLSI are all the same. So at some level, you have a very homogeneous substrate to begin with, and that's how computing started. But we build on that enormous amounts of diversity. So first of all, we have at the hardware level, we build different chips that are memories and interfaces and stuff like that are completely different from each other. Even though if you look below, they're all the same. And then on top of that, we have an operating system. And on top of that, we have all these application software. So those are layers stuck on top of a homogeneous substrate. So we deliberately create this enormous diversity. But then in some ways, we hide it again. So if we're sitting here doing Zoom, we don't see all that diversity. We won't see all the fiber optics and all the routers and everything else. We just seem to be in the same room. So what that architecture does is it makes you robust to the hardware levels, which if you actually looked at what's going on in your chip, like with analog signals in your laptop, it's a god-awful mess. I mean, it just looks like noise. But if you pop up a level and look at it digitally, it's like perfectly reproducible. But then that's not useful. You've got to put an operating system on it. You got to put an application layer on top of that. That's a layered architecture we understand. Everything is like that. Everything has to be layered like that. If in order to create systems that are flexible, like software, fast, like the hardware, but also robust, which the operating system delivers. So in the last session, I was saying we need to think about architecture if we're going to be slapping learning on stuff. But here, we need to think about that kind of architecture to understand a system like this. And this is fantastic. Again, Eve is a hero of mine. And this is a fantastic example because this neuromodulation is a layer of control that sits on top of the spikes. Much slower. It's a little bit like an operating system element in that it creates this platform on which you can do all sorts of things. And I would love to pursue that further. What Terry and I have been focusing on is sensory motor control in humans, which has to be layered or you can't do anything. It has to have enormous diversity. Okay.
So touching on the components at the bottom, this is something where I think Guillaume has contributed a lot, along with Rodolphe and others. That when you look at the conductances that are present in a neuron, you find that, yes, that they all have different biophysical properties, but when they get lumped together in a single cell, you find 3 or 4 main timescales or major motifs. So you get, as Rodolphe has talked in his introduction, you have this nested motif of positive feedback and slow negative feedback. You see that at the level of single cells. You also see it in circuits. There's a lot of
yes, absolutely.
In delayed inhibition and sort of center surround inhibition at the circuit level. So you see the same almost Hodgkin-Huxley-like motif repeated. So is that part of the answer? Trying to understand really, the dynamics in this sort of nested way?
Well, one of the things that's so exciting about Rodolphe's work is he really shows that spiking neurons are this fantastic device that sits between digital and analog and lets you have features of both with one piece of hardware. And I still don't understand all the implications of that. But it's clearly a case where as hardware, it's really slow and it's really inaccurate compared to digital VLSI. But it has this rich digital and analog behavior that allows it to be slow and sloppy and do amazingly robust things. And again, just beginning to scratch the surface of that. And so I know what's going on in your laptop, but I would like to understand what's going on in the brain. And I think with Terry, we've looked at the big picture architecture in a way that we'll be able to plug Rodolphe's stuff in, but we haven't done that yet. But that's a crucial area.
I would just like to add one little complication, which is the neurons in the stomatogastric nervous system, like some neurons in humans and rats, etc., operate with graded transmission so that they actually release transmitter starting at very hyperpolarized membrane potentials, and they don't require spikes in order to release transmission. So they are really computing in the neuropill as an analog device, and then they're using the spikes to send signals over distance. And I think this mixture of having the same neuron be both an analog and a digital computing device is also really, really important. And, you know, that's sort of pulling together different time scales. It turns out it's much easier to be very reliable if you're computing in analog, right? Without slow oscillations, then you're much less hostage to when an individual spike fired or didn't fire. So I think if you have a rhythm, which you really want to be the rhythm to persist, computing in analog is really helpful. It also makes you immune to the details of where individual synapses occur in a neuropill, which is, again, a tremendous advantage. So I think, John, we could talk about that, I mean, because these things really are both analog and digital devices.
Oh yeah, that was the essence of my point, which is that this is a really remarkable device in the sense that it can compute mostly locally in analog, but then it can do long range digital packet switch networks. I mean, that's astonishing that you have have hardware that gives you that capability. And engineering is going to go that way, in the sense that we're going to get back to doing a lot more analog computing, and a lot of the people who are in this workshop are working on that. And so, and also obviously quantum is another resource that's going to be important in computing. So computing is going to get much richer than it is now, but already computing creates diversity out of a homogeneous substrate by layering, like I said, chips and then operating system. And then, so the question is, I really don't still get the essence of what Rodolphe is doing or what you're doing on what's analog, what's digital, and why. And I think there's low-hanging fruit there, in the sense that sorting that out in some simple systems. And I think like Fly Escape, I think your system, Eve, is great. There's a few canonical things that have been studied very well, and we should start looking at what's analog, what's digital, and why.
If I can just John and Eve, to stress the importance of this topic for this workshop. I'm rather new in the world of neuromorphic, but my recent collaboration with Gert has really, I've been really surprised to see how much analog systems, analog VLSI systems, have the same variability as real neurons. And, you know, I was thinking that VLSI, you said, John, at some point that transistors are all the same. But the truth is that when you operate transistors in this analog regime, you have just the same degree of variability as Eve described in neurons.
Oh yes, absolutely. No, I meant the digital interface hides all that.
Exactly. And I think that's
for good and bad. For good and bad.
That's what's fascinating in neuromodulation, is that it's really making analog regulation, but at the same time allowing for this digital reliability. And that's really what's, I think, we want to learn from biological neurons.
So I'm aware that we've reached a time limit here. I don't know how strict we want to be. I don't want to get fired. Should we pass on to the next speaker? Are we ready to do that?
Let's. Eve had a point, so Eve, please.
I just have one more point.
So let's have one discussion point, and then
we'll go. So my neuropill computes an analog. The motor neurons send a digital signal out to the muscle. These muscles actually don't have action potentials, and so they have graded contraction, which depends on the frequency and the properties of the motor neuron discharge. So you have analog, then digital, and then you're going back to an analog transform for the movement. And I think, John, you should be fascinated by the fact that you go from analog to digital to analog to produce the coordinated movements of the animal stomach. And
Oh,
so,
that absolutely, because that's how airplanes work. We start with analog signals, compute everything digitally, and then have analog actuators. And so more or less you have to do it this way if that digital part has to be long range. And so this is I mean, again, fabulous system. I'm eager to learn more about it. And I got sort of sidetracked, I think, effectively with Terry on, you know, sensory motor control in humans, but I think this is a great system to study exactly this thing you just said.
Okay, well, thanks everyone. It would have been nice to keep the discussion going because we barely scratched the surface of these questions. I think it's safe to say we can answer the final one in the negative at this point, but there's plenty to do. So
we'll
I
have some
should
more
pass
discussions later, right? Over
yeah,
over
absolutely.
talk,
Plenty of stuff to discuss. So I need to pass on the screen share, I think, or someone will take it from me.
Yeah, so let me then first look for the next speaker. Is Marcello Ienca present? Oh. It's not.
I don't, hi Shichi, I don't see him actually. So maybe we should write him, get a chat, and you guys can go on a bit with your discussion while we get him here on the Zoom and make sure that he has the link. Is Andreas there?
Yeah,
or
it's
who is
Andreas there.
But I invited him, so I will take care.
Cornelia, yeah. Could you send him the Zoom link, just copy from the, cool. And then you can go on and discuss a bit more about the neuromodulatory control.
Sure. Okay.
So I can just make
as soon as the speaker shows up, just butt right in.
Shichi, Shichi.
Yeah, I just want to make a point from just from the analog technology side, and Good can pipe in also. So the variability that you see in the analog VLSI circuits is frozen, right? So when you get a chip back, you see the variability and it's frozen. By biology, it's not, right? Biology consists of living cells that would tune the parameters continuously. There's a lot of feedback going on everywhere. You know, John Doyle will love this. You know, so it's true we're building circuits. We can build analog circuits, but the one thing that we can't change is that when the circuits come back from the fab house, you can't change the transfer function.
Not quite, right, Chichi? So, well, first of all, there's one rev noise, right? Of course, that's
unless you purposely, you can do things to amplify the one rev noise.
Right? Radio telegraph system noise, right? But there are also the floating gates. So Jennifer Hassler, right, is here too, and they have this other workshop, right? Or this other the Ienca, right, workshop. So you can also use floating gates and other mechanisms, residual RAM, etc., right, for changing non-volatile changes, right, in connectances, right?
Yeah, no, it's true. You can change the properties, but it's a bit more clunky. Yeah. I mean, biology is just beautiful, right? If something doesn't feel right, then then the adjustment is just made right away. You don't have to count on some delays, setting a bunch of pulses so that you can change the conductance of the of a resistive element. It's just different that way, right? I mean,
and when Carver started the field, right, he really asked us to listen to technology, and so floating gates and other mechanisms for adaptation were key in neuromorphic engineering from the very beginning. Right, and it's only now that we're embracing learning and adaptation in those systems. But I guess the point here in the panel, right, is that neuromodulation is one mechanism that should have been explored more centrally, right, in all those adaptation mechanisms, right, for regulating function, right, in neuromorphic systems, and we should see more of that.
So in fact, that actually reminds me of something Kwabena Bohan told me a few years ago, which is that in their chips, they do have time-varying variability due to temperature. So they have this really annoying form of variability where the characteristics of all the components change as the chip is being used. And that's also a problem in the biology. So there's a really interesting link between actually Eve's work, showing that you can think of temperatures as a modulation, if you like. It's an annoying one and possibly one that's you don't want. but it looks like the biology, and Eve would comment better on this, does have neuromodulatory compensation that combats the effect of temperature. So this.
But wait a minute. Is it possible that neurobiology is also following very simple strategies, such as in compensating for temperature, where the operation of the circuit only depends on the ratios of currents, and those ratios remain constant with temperature? That's how we do it with our.
Constant. They don't remain constant. Every single protein has a different temperature dependence. The whole point is, if everything had the same, what we call a Q10, then you'd be fine. But every single ion channel has a different Q10. So you have a really interesting problem of stability because they're all different.
Well, actually, I have a follow-up question to that. I mean, in analog circuits, you're kind of not only frozen with the offsets, but you're also frozen with the interconnectivity. And I was wondering if you have this high redundancy of different information channels, like ion channels that essentially add up to the same function, but change over temperature. The ratio changes over temperature. Are these? I mean, if you're trying to transfer information, for example, by hormones which modulate the behavior, is the diffusion constant, the temperature dependent kind of range and strength of these channels is how do they work, and are they is it actually the transport properties where the different temperature dependencies kind of add up to have the same effect over a wide range of temperatures?
There are lots and lots of different time scales in all nervous system functions. And so temperature, so if you have 10,000 proteins in a cell, each one of them will have a characteristic temperature dependence of its function. And as you go through a 15 or 20 degree temperature range in a cold-blooded animal, you're going to be moving through this very complicated shape. So you have a lot of degenerate mechanisms. So you can cover up or compensate for a lot of that stuff, but eventually things will stop working. Now the modulators, I mean, the timescales, modulator timescales are slow relative to action potential timescales. Action potential propagation is pretty fast.
The equivalent to timescales in time are kind of diffusion constants in space.
Yeah, but that's usually pretty. Depends on obviously whether you're talking about putting a hormone into a whole animal, which might take minutes, or whether you're talking about diffusion over 100 microns in a small neuropill, which will be very fast.
So what I wanted to say one thing about this temperature issue, which is if you look even at E. coli, they're very sensitive to temperature, but they compensate for it with fairly complex networks. And early on, these networks were thought to be redundant. There's so many loops, it's redundant, and it's not redundant, it's diverse. So each mechanism operated on a different, sort of different speed accuracy. So there was really fast mechanisms that are a bit sloppy, but would protect you when you had a really fast transient change. And then there was slower, more accurate things that would fine tune that. And even E. coli has this layered architecture for compensating for temperature. And so I think that's the rule rather than the exception, that the complexity that first appears gratuitous or redundant is actually to create diversity and to create these things that Terry and I call diversity-enabled sweet spots, where you get speed and accuracy that no part has by combining fast and otherwise slow but accurate components.
So heat shock proteins are another good example. They're very rapid and they help protect.
Yeah, it's heat shock. It's the controlled heat shock proteins, but they're controlled both at the RNA and at the protein level. And so it's a really interesting layered architecture.
Okay, I'm going to take the bull by the horns and just impose a break now, because Marcello is on the way, but everybody needs a break. Just like the 21 dealers and craps dealers in Las Vegas can do 40 on, 20 off, we're tougher, so we can do like 120 on and 5 minutes off, but we need a little break. So I propose that we wrap up the session now.
Great. Thank you, everyone.
Thank you. It was wonderful.
Thank you.
Oh, Marcello is here. He's here.
Yes.
Oh, okay. Okay, no break.
Sorry.
Once
sorry,
again.
late.
But I think
got
we'll,
my
yeah,
second
Cornelia, are you there?
Yes, maybe we'll take still the 5 minutes.
Yeah, I think we
You're
should
going to
take
take a 5-minute break while
Get a
things
file
get set up.
break.
Yes,
File-
Marcello had a reaction to his
Yeah.
COVID vaccine, so.
Oh, no.
Or, yeah, he's got the fever, right? The 2-day fever. Or longer.
Yeah, no, not yet. I actually got the job really 1 hour ago, and I had a minor allergic reaction, so I had to stay under observation for a longer time, and that's why I'm a little
Yeah, I
bit.
know.
Okay, all
I've
right.
heard
So
about
we're
that.
back at 7:18. All right, for 5 minutes.
7:18.
Yeah.
Okay.
All right.
Good.
Till then. You could pause
Remind me to
recording. Sylvie.
unpause the recording then, okay?
Yeah.
Eva, I'm just going to quickly say hi and then disappear.
Okay, how are you doing?
We're hanging in there. Nia got a temperature today, so she's home from the nursery. We have to self-isolate.
Oh,
Hi, Sim.
you don't think it's COVID? You think she just got the flu?
No, it's a toddler thing, just germs. But we have to self-isolate. So
I
I'm
think
going to
that's
go down.
very wise. What? Yeah,
I was just saying I'm going to go down and help. I'm needed on deck.
I would think so, because
So
she
we'll speak
probably.
soon. Good to see you, Sim.
Yeah, you too, Tim. Yeah, it's surprised to see you here, but that's great. Yeah.
Yeah, no, but yeah, I remember you went into Neuromorphic Real SI early on, right?
That's right. Yeah, yeah. I've been banging out chips
With
for
Alan Murray.
years or so. Yeah, that's right. Yeah.
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 Good to see you in Colorado.
Yeah, absolutely.
And Tim, we should talk soon.
Yes. Yeah. Okay, I'm going to sign off. I have to run. Thank you.
Okay, bye.
Bye, guys.
That was a great talk, Eva. Very much enjoyed it.
Oh, thanks.
Yeah.
You know, I'm not going to be able to sit and listen to the whole workshop, but if there's any point that you want me back, just send me a note. And
Yeah, in fact, so Rodolphus and I are organizing for the, so we have about 120 participants in this workshop. And so I guess we're all scratching our heads, so what type of projects we're doing. And so we definitely like to integrate, right, with your work. And so there's several example projects or tutorials that we really put together for participants to try out these different small networks, right, that do some of that emulate that polaric rhythm, right, with a few neurons here and there. We're having a meeting after, in fact, in about at 11 here, which is that would be 2 o'clock Eastern time. I think it's 6 p.m. GMT. I know you don't like Slack, so we had an announcement on the Slack, but I can share this.
no, I don't. I'm not doing Slack. I mean,
I know.
I'm just on. I'm on Slack strike.
I totally understand. I'll send you the. I'll send you the Zoom
You know
link.
why? You know why? It's just more passwords.
Yes.
I'm on Slack strike. So let me just check my calendar. Hold on. I have a meeting at 3:30 today, my time. So you're telling me this would be 2 o'clock my time?
Yes, that would be perfect if you can join in.
Okay, so you want me to log back into the same Zoom?
I'll send a link to.
It's a different Zoom link? Yeah.
It's a different Zoom, yes. Rodolfo.
Okay.
Yeah.
Okay, so send me the Zoom link and call it 2 p.m. and I'll come back at 2.
Perfect. Thanks.
Okay.
Thanks, Eva. Yeah.
Okay, bye.
So Gert, where is the complete schedule for all of the different events?
The complete schedule?
For the neuromodulation. So I don't have this. I don't have this 2 o'clock session that Eve's coming to. It's not listed in what you sent me.
I'll send you a invite on
Please check, Cherry, it's just like the real Telluride. Schedule actually changes day to day. So the only authoritative schedule is the one that you see on the schedule page.
And
that is only authoritative after the event actually started.
Well, Terry,
Look on the schedule page, right? If there's some mistake there, let us know. We'll fix it.
Well, that's the overall schedule. Now, Neuromodulation Control has also a schedule of side meetings. And we have one today. So, but it is in the Slack, Terry. So we have that, and I'll send you also that.
I think you should just put it on the main calendar.
Oh, okay. Good idea.
Yeah,
we'll
just
do
add
that.
them.
Yep.
But color them, according to the code, right? So it's easier.
Do we have right access to the calendar?
Yeah, you have right access. You just never used it.
Okay. Okay. Right. Thanks. Good. Great.
Okay. So, Cornelia, Marcello, you ready?
Yes, I am.
Okay.
So just give me a second to share my slides.
Yes. And Cornelia, you want to say a few words? See, I've lost her too. Cornelia?
Okay, so we have here with us Ienca Marcello from ETH Zurich, whose work has been in big data, ethics, ethically aligned AI, and neurotechnology. So he's the right person to tell us about ethical issues in neuroscience and neuromorphic engineering.
Thanks for the kind introduction. Can you hear me? Can you hear me and can you see my slides?
Yes.
Perfect.
See the slides too.
All right. So my presentation will focus on the ethics, as you rightly heard from Cornelia, and the interplay of neuroscience and AI from an ethical angle. And I wanted to start with a quote that dates back to 1960s to paper entitled Man-Computer Symbiosis by G.C.R. Licklider, as you all know, one of the fathers of modern computer science, who about 61 years ago wrote that the hope is that in not too many years, human brains and computing machines will be coupled together very tightly, and that the resulting partnership will think as no human brain has ever thought and process data in a way not approached by the information handling machine we know today. Now, if we look at the history of computer science, we know that this history is full of predictions that turn out to be wrong, mostly due to excessive optimism. I think this is one of the few predictions that turn out to be correct. And there are two main ways through which human brains and computing machines are being coupled together very tightly in recent times. One is through the so-called brain-computer interface channel, which increasingly enables opportunities for direct communication pathway between the human brain and external computing systems, in particular in a manner that bypasses the peripheral and neuromuscular system. And secondly, we see this tight partnership between neuroscience and AI in the field of neuromorphic computing. Here, the task is not so much to assist or stimulate the brain, but to simulate the brain at the functional level. Now, in the interest of time and for the purposes of this meeting, I will focus my presentation primarily on this latter aspect, on simulating the brain and the ethics of neuromorphic computing. But I'm also happy to discuss the ethics of brain-computer interfacing in the Q&A. Let me start with this. So in recent times, and I'm pretty sure that many people in the audience are familiar with this trend, ethics has become prominent in the AI domain as more and more organizations, public policy entities, as well as professional associations have developed or issued AI ethics guidelines. And this is a response to public concerns related to the relevance of AI and its increase in both market size and implementation and societal applicability. In order to map this ever-evolving field of AI ethics guidelines, we conducted a meta-analysis of documents in which we tried, together with Anna Joban and Effie Vallena, we tried to map the various ethical principles that are being discussed and promoted through this AI ethics guidelines. We also saw that most documents are being currently developed by entities operating in the public sector, such as governmental organizations and IGOs, followed by organizations in the private sector, such as companies and private sector alliances, as well as academic and research institutions. Now, the thematic analysis that we conducted revealed that there is no single ethical principle that is common to all documents. So we couldn't find a full convergence of these ethical guidelines, but we could identify 11 overarching themes that are dominant and that have been mentioned by more than 50% of documents. And these are the principles of transparency, the principle of justice and fairness, non-maleficence, responsibility, and privacy. We also expanded this analysis as part of a work that was commissioned by the Council of Europe, which, as you may know, is the organization in the European regulatory space that is aiming at developing a legally binding framework on artificial intelligence, including on research and medical uses of AI. And also in these guidelines, we observed that most guidelines tend to agree on some generic ethical principles, and they pretty much match the principles I mentioned before. But they sharply disagree over the details of what should be done in practice. So what can be done to implement these ethical principles in practice? In other words, we are seeing a huge debate, but very little consensus. Also, one interesting aspect is that in all these AI ethics guidelines, neuromorphic computing or neuromorphic engineering is being mentioned only 3 times. So in only 2.5% of the corpus, indicating that this is an area of computing that is not particularly of interest for ethicists and regulators. And of course, it also suggests that ethical reflections of neuromorphic computing are somewhat in an infancy stage. There are notable exceptions, of course. One of those is the Human Brain Project, which issued a call for ethics training events. In particular, the HPP Foresight Lab organized a workshop with the Neuromorphic Computing Sub-Project, which was focused on practical ethical questions with special focus on dual use. And I'll mention in a second what dual use is in ethics literature. I also wanted to highlight that this relatively underrepresentation of ethical concerns and ethical reflections related to neuromorphic computing may well be a consequence of a well-known dilemma in technology assessment studies known as the Collingridge dilemma, which is basically a double-blind problem, which is a function of 2 conflicting constraints. One is an information problem, namely the problem that the impact of a technology cannot be easily predicted until the technology is extensively developed and widely used. But at the same time, there is a problem of control, namely that controlling or modifying a technology via governance, regulation, ethics guidelines, and so on It's much more difficult when the technology has become societally entrenched. So the big challenge for ethics and the law is striking the right balance between acquiring sufficient information about a certain technology or certain socio-technical trend on the one end, and having enough power to shape the use, design, and implementation of such technology at the societal level. Now, there are many ethical schools and many approaches to ethical thinking. One approach to ethical thinking that may be particularly relevant for our community and this debate is the utilitarian perspective. Namely the idea that the ethical value of a technology should be assessed based on its ability to produce the greater welfare for the larger number of people. And therefore, the greater the welfare and for the larger number of people, then the greater the ethical value. And I think from this perspective, we can safely argue that the ethical value of neuromorphic computing must be assessed by its contribution to benefiting general human welfare, and therefore maximizing utility. This is an ethical approach that dates back to the work of David Hume in the 18th century. And I think a lot of research is showing that neuromorphic computing can have a big utilitarian value, in particular because it can produce a double epistemic benefit. On the one, it can help us improve AI through the study of the brain, but at the same time, it can help us improve the study of the brain through AI. This is something that has been nicely put in by Shimon Ullman in Perspective in Science a couple of years ago. Also, in order to assess this utilitarian value, we need to consider the practical value that enhanced computing can have for the social good. And we have plenty of examples of vision systems, auditory processors, autonomous agents, and bio-inspired robots that can generate substantive benefit through a variety of clinical and non-clinical applications. So this is something that I often emphasize with our medical ethics students. Namely, ethics is not always about restricting scientific innovation and technological innovation, but it's about aligning scientific and technological innovation with societal values. And here we should be reminded that delaying a beneficial technological innovation is not a neutral moral position, but one that may reduce human welfare. Also, there is a potential utilitarian benefit associated with neuromorphic computing in terms of reducing high energy consumption and carbon footprint. There is some ongoing research on the carbon impact of AI, and there is also some research that is showing that computations that, for example, involve deep learning models may have a high carbon footprint. But there's also research that shows that bio-inspired models that can actually be more energy efficient than differently inspired models. So this is also a variable that may play a role, especially from an environmental ethics perspective. One interesting paper in this domain is an analysis by Schwartz and colleagues, which looked at 60 papers from top conferences and concluded that the vast majority of those papers are prioritizing accuracy over efficiency. And they distinguish red from green AI applications. Red AI are those that are buying linear gain in performance through exponentially larger models and larger amounts of training data, which of course will result in escalating computational costs and carbon emissions. Whereas other models, which are labeled by Schwartz and colleagues as the green AI, use the inspiration of the biological brain to make models that are more energy efficient. Also, they observe, this is Greatrix, who also wrote an interesting paper on the ethics of neuromorphic computing, argued that neuromorphic computing holds potential for drastically reducing the energy used in data processing compared to conventional computer, because of the increasing amount of data processing that can be done on individual devices, therefore reducing the need to send data to data centers for processing. Now, this is very important because compliance with environmental goals is at the forefront of AI ethics today. Most international organizations are pursuing this goal of increasing the energy efficiency of AI models. There was recently a consensus-based expert elicitation looking at AI models, and this resulted in developing the so-called sustainable development goals. And what we can see is that current AI models can help accomplish some of the sustainable development goals, but they also inhibit some of these targets. So there is more work to be done. As you might recall from our meta-analysis I showed before, fairness and global justice were also a prominent ethical consideration. So promoting human welfare in a just way is an ethical priority. However, it is an open question whose welfare should be promoted. If we see if we look at the current race for AI leadership, we see that it is affected by profound imbalances, power imbalances, and economic imbalances at the global level, with some areas of the globe, such as Africa, for example, being profoundly underrepresented compared to other regions, such as Eastern Asia, Europe, and North America. And this is an ethical problem because an unfair distribution of AI may lead to an unfair distribution of the benefits of AI. So the goal should be pursuing global justice by benefiting the largest number of people in the largest possible way. There is also a challenge of public perception, which seems to be peculiar to neuromorphic computing compared to other approaches to computing and AI in general. Interestingly, some survey data, both from the Eurobarometer and from United States survey, show increased concerns and negative public perceptions towards machines that are able to mimic or replicate human functions. More work in cognitive psychology needs to be done to understand the causes of these concerns and negative perceptions, but this seems to be an empirical fact, which is also something that we need to take into consideration. Also, another reason for ethical concern among the public is the reliance on animal models in neuromorphic computing research. And here the debate is rapidly shifting towards looking at risk-benefit assessments in a more longitudinal and holistic manner. And from this point of view, bio-inspired computational models may provide us with extra tools to explore how the brain works and allow us to partially obviate the need on the long term for ethically challenging animal models and human subject research. However, we always need to be reminded that the validity of simulated models must be first tested and benchmarked against conventional in vitro, in vivo, and clinical models as research ethics guidelines entail. Also, the risk-benefit evaluations based on proxy informations, such as practical use or previous history, might be unsatisfactory because they risk penalizing basic research with little short-term application. So this is important to avoid a bias towards applied research as compared to basic research. I mentioned dual use earlier, which is at the focus of the 9th work package of the Human Brain Project and the ethics working group. Dual use is basically the tendency of any technology and any life science research to be potentially subject to risk of misuse. So to be co-opted for purposes that are different than the purposes that were originally conceived at the time of developing that technology or conducting that research. And one typical example of dual use is the risk of military co-optation of civilian research or other repurposing. This is a risk that is particularly cogent both to neuromorphic computing and brain-computer interfaces. Departments of defense worldwide are relying or either directly relying upon or funding research in this domain. In my view, this is not ethically problematic per se, because as we argued in this paper you see here on the right, historically observed a lot of innovation in computer science and biomedical technology that was originally produced for civilian applications and subsequently co-opted for military research, then at a later stage further spill over onto into the civilian sector through new clinical or commercial applications. So this is the reason why a moratorium or an outright ban against military research in either neurotechnology or neuromorphic computing could have more detrimental than positive consequences from a human welfare and social good perspective. But at the same time, we are currently lacking standards for military reuse and dual use in general, compared to other domains of science, such as say virology or bacteriology. These are domain of the life sciences where they have biosecurity frameworks and established best practices for reducing risk of non-civilian co-optation. We do not have similar standards in neuroscience and computing to date. Another ethical approach that is relevant here is deontology. Here, compared to utilitarianism, the goal of deontology is not maximizing human welfare, but complying with a certain set of basic norms. And these norms usually reflect duties, hence the term deontology. Deon means duty in ancient Greek. Here, we can identify the following 4 challenges. One is the challenge of establishing public trust and fostering well-grounded public expectation. A second is producing clarity about current and future technological capabilities. And here is something that the media often get wrong, and they do not help us as scientists to engage the public in a transparent and an accurate way. Third is exploring options for enhancing access to neuromorphic computing in order to increase global justice. And fourth is defining standards for ethical and responsible design. So let me start with the first one, establishing public trust. Establishing public trust is a key requirement for the societal adoption of any technology. We do have a moral responsibility to avoid at the same time industry-driven hype, which is a fact. Again, there is ample research that shows that companies are exploiting the hype that the buzzword AI generates in order to increase return of investment. There are interesting surveys that show that companies that use AI in their business mission, they tend to receive more funding ceteris paribus compared to companies who do not do so, even when such companies do actually do not produce any AI in any significant sense. There is also a responsibility to avoid media-driven fear-mongering narratives that could lead to public misconceptions, the typical narrative of AI systems taking over the world, or in more recent times, as applied to brain-computer interfacing systems, the conspiracy theory that the BCI industry is aiming at installing chips in people's brain in order to control their minds. As a small anecdote, many BCI researchers are actually being snowed under emails from people who actually report having their thoughts read against their will because of the existence of BCI technology in the world. And also we have a responsibility towards avoiding philosophically dismissive attitudes based on unclear time frames. So on the one end, we have this media-driven narratives that say computers are taking the world and they're coming for us. But on the other hand, we have this radically dismissive claims in the ethical space of people who argue that certain AI-related risks are impossible. And again, this is an apodictical claim that is loosely rooted on empirical evidence. So we really need to navigate these ethical scenarios with an awareness of uncertainty and with an evidence-based approach, rather, with this apodictical thinking. Then there's this obvious elephant in the room, which is about defining with clarity current and future technological capabilities. Many people have argued that neuromorphic computers might accommodate artificial general intelligence and synthetic consciousness. And this is, as you know, synthetic consciousness and AGI is a topic of major interest for ethicists. And other people, as I mentioned before, have dismissed AGI as a science fiction at best, or an irresponsible distraction at worst. That was a quote from Tadeo and Floridi. As I was trying to argue before, I think we need to have a more intellectually humble approach to ethical debate based on both theoretical and empirical evidence. I want to conclude with a few words on the time frame of transparency, because we do have some research, some surveys of researchers' attitudes and expectations about the realizations of AGI. Such as this survey by Miller and Bostrom. As you can see, the majority of computer scientists tend to think that we will reach human-level AI in more than 50 years, and an equally large portion of researchers thinks that we will never reach that. But if we look at the next question, so the earliest we will understand the basic operation of the human brain sufficiently to create machine simulations of thought, then the number of people who think we will never understand enough the brain to simulate it in silico, then it drops significantly to between 19 and 21%, whereas the majority of researchers do think that we will be able to reach that point within a century at the most. And the final point I wanted to discuss before moving to the Q&A is the ethical importance of developing science-based standards for ethical and responsible design for neuromorphic systems. I was making a cross-disciplinary comparison earlier in the presentation, for example, with molecular biology, where they have very established standards for biosecurity and for preventing the malevolent reuse of basic research into ethically questionable applications, such as bioterrorism and so on. We don't have the same established standards in neither in neuroscience nor in computer science, and that's the bad news. But the good news is that we are working on it, and there are two main communities that are attempting to do so. One is the neuroethics community on the one end, which is attempting to develop ethical standards for neurointerventions. And then on the other hand, we have the AI ethics community that is attempting to do so for machine learning models and other approaches to AI. The problem is that these two communities are not sufficiently interacting right now. I think there is a need for more interaction between our communities in order to address the ethical challenges that are emerging at the interface of neuroscience and computer science in a more holistic manner. Also, with regard to developing science-based, evidence-based standards for ethical and responsible design, there are several attempts that have been pursued. This is an attempt by Thomas Eve and colleagues, who defined 10 steps towards developing such standards with special focus on neuromorphic systems. We are also working on developing such standards in collaboration with international organizations such as the International Neuroethics Society. And here we're doing so with special focus on applications of both neurotechnology and neuromorphic computing that may result into clinically beneficial systems. Here, one aspect that I wanted to emphasize is this conceptual shift from an understanding of ethics as a limiting factor or as an oversight, a pure oversight mechanism that is designed to police on science, and shifting towards a conceptual understanding of ethics as a facilitator. In other words, ethics, I think, can and should be increasingly seen as a collaborative knowledge system that can help us maximize the beneficial potential of new technology or computing trends, mitigate their unintended risks, and manage their impact on public opinions, and also shape evidence-based science policy in a manner that can bridge translational gaps between the various communities. So I will stop here, and I'm happy to take any question. Thanks.
Thank you, Marcello.
Yeah, that was very illuminating. Could I ask a quick question? So I think, you know, it's interesting asking people to extrapolate 100 years from now. The fact is we're not very good at that. Humans are incredibly bad at imagining the future. So who could have imagined the impact that the internet would have back in the 1990s, right? It's only 30 years ago, and already it's completely changed the world and unintended consequences. And I think that's the problem, the unknown unknowns. That's really what I think will have the biggest impact up the road, and we can't really even imagine it now. So how are you going to handle that?
Yeah, I think you're absolutely right. We need to navigate uncertainty, and that's complex. As scientists, we're already used to navigate a high degree of uncertainty. When we translate science into society, then the number of variables that generate uncertainty is even bigger, because societies are complex systems that tend to act in a stochastic manner. And if we look at the history of computer science, I mentioned this earlier in the presentation, we see a long sequence of bad predictions, even by the most brilliant minds. I recall Herbert Simon arguing in the mid-1950s that we will reach human-level intelligence, human-level artificial intelligence that will be able to accomplish any task a human can accomplish within 20 years. So it was predicting we would achieve that in the mid-1970s. And now we are in the 2020s, and we are still far away from that. So if Herbert Simon, one of the greatest minds in our field, was making such shockingly inaccurate prediction, I can really not offer any more accurate prediction than this. What I can say, though, is that uncertainty is not at odds with knowledge. Knowledge generates, uncertainty can generate knowledge, and our knowledge originates from uncertainty. What knowledge is basically reducing ignorance. And we have been doing this consistently over time also in relation to ethical challenges. But I think in order to do so consistently, it's very important to see ethics as an ancillary discipline of science that shares the basic methodology of science and therefore proceeds in an evidence-based way, rather than something that is entirely based on either subjective opinions, personal feelings, or political or religious views. Because if we look at ethics in this way, we can make some small but regular progress. And the problem you just described is the problem that I also mentioned in the presentation, that this Collingridge dilemma. So on the one end, anytime we have a new technology, we have very little information available in order to make accurate prediction about its future development and societal impacts. But if we wait too long, then we will have collected a lot of information. We will be able to make very accurate predictions, but those predictions will be probably too late to shape public policy. You know, if we look at socio-technical trends such as social media, for example, you know, social media 15 years ago were probably on the information problem side of the Collingridge dilemma. So we had limited information about these networks. We didn't know what kind of impacts they could have on societies. But now we have a lot of information. There is a lot of research on computational social science and the impacts of social media on democratic processes and also their impact on the psychology of minors and so on. But this socio-technical trends are so much entrenched in our society that we have very limited power to control them and to reshape them through ethics and regulation and so on. So the big challenge is striking the right balance for intervening between having sufficient information and having still enough time to steer the direction of a certain socio-technical trend in a manner that is aligned with the public good.
Thank you.
Any other questions? Cornelia?
I'm also happy to take questions that are not directly related to the presentation, but to ethical issues in general related to your own research or other dilemmas you face.
Yeah, let me check on Slack quickly. See if any questions, because some people ask them over Slack. What is G index? No, I'm not sure. I don't understand Crystal's question. So, yeah, I feel like this points that you bring up are actually very relevant to any research area that works on AI, right? It's not just neuromorphic engineering. So is this how you also interpret, you know, the sort of the role of neuromorphic engineering? It's not specific to this one research field.
I think you're right. I do not think that there is something inherently or qualitatively different in neuromorphic engineering from an ethical perspective. But there might be something different, and this is something that I tried to stress in the presentation, from public perception perspective. So as you might recall, I was showing some survey data that show that people both in Europe and in North America tend to be more concerned about AI systems that mimic or simulate the human brain. As I said, we don't have enough in-depth research to know why this is the case, but the mere fact that it is the case generates additional responsibility for us as researchers, and also additional challenges, because we know that our research may be facing increased opposition or at least skepticism within the public sphere. And this skepticism is worrisome because it could lead to either exceedingly restrictive policies in the next few years, or just a public misunderstanding, which also may ultimately result in a reduction of funding. So this is something that we should be concerned on. Then I think another issue that is more peculiar to neuromorphic computing compared to other areas of AI is that neuromorphic engineering has a greater reliance on animal models because of the need to mimic biological brain circuits. And as we all know, animal models are an ethically challenging topic, a topic that tends to polarize public opinion. And then finally, there is this conjecture that by mimicking the biological neural networks through artificial ones, we have greater chances of achieving artificial general intelligence. And then artificial general intelligence, as you all know, is also an ethically heated topic. But again, I don't think that these are difference in kind. There are more difference in magnitude, in the way ethical concerns in the public spheres are phrased and uttered in relation to neuromorphic computing compared to other areas of AI.
Yeah, I understand. Yeah, it makes sense.
Could I ask for some advice? So, by the way, there was a talk at NeurIPS a couple of years ago on ethics and regulation, and basically what the speaker said, I've forgotten who it was, but I think it was someone at Yale, said that if we don't debate amongst ourselves of what of what the consequences are of what we're doing, that the government's going to step in and regulate it for us, and they'll probably be more heavy-handed. And so we have to be at the table. We have to, and biologists have already done this when recombinant DNA technology became possible. They had a Silomar meeting where the top molecular geneticists got together and came up with the idea of having different levels of P1, P2, P3, P4 of containment, so that things don't get out into nature. And if we don't do that ourselves, somebody else is going to do it for us. So I think that it's very important that we have this discussion. But the advice I need is the following, and it has to do with sponsorship. So I'm the president of the Neural Information Processing Systems Foundation that runs the annual meeting. This last year, we had 26,000 people at our internet, all online meeting. And one of the issues that has come up is the sponsorship. The National Security Agency, for example, wants to be a sponsor, and we've been open to anybody up until recently. But there's really a vocal group that thinks that any company that is using AI for surveillance or for military purposes should be excluded from being a sponsor. And where do you draw the line? Because it turns out that almost every research that anybody's doing could be used for, of course, other purposes. And so, what do you think about that? Should we exclude sponsors who are, and why? I mean, what's going to happen?
Okay, maybe to expand on my remark or question, I would suggest a line, which is actually the line that's called the Gini coefficient, which is basically a measure for the inequality of any good or service, or which is it's a measure of the artificial scarcity. So as a rough orientation, you can say, will my contribution produce artificial scarcity? Will my contribution produce exclusive an exclusive distribution of my work product? So I mean, the NSA, for example, wants to have exclusive information that only the NSA itself, not even the government, has full access to, and the general public doesn't. So that is an ethical message, an ethical measure is the result, how equally does everybody benefit from the result of my work? And that's not so much what do I do, but whom do I give control? So that's my suggestion. Take it as you want.
Yeah, I think you both raise very important issues. So going back to Terrence's previous point, I think you're absolutely right. If we do not discuss these issues within our own community, people will decide for us. If you pass me a politically incorrect statement, science and technology policy is too important to leave it in the hands of politicians alone. And I think it's very important that scientists, engineers, possibly academic ethicists sit at the same table with politicians in order to make sure that public policy development is done in a science-friendly and evidence-based manner. And this is not always the case. We have an uncountable number of examples in the history of science and public policy where we see even scientifically literate countries pass bills that generate undue obstacles to science. And this is, again, the reason why I always tell my students, ethics is not always about policing on science, because delaying delaying the technological innovation that is societally beneficial is not ethically neutral. It's detrimental. If we delay the development of technologies or scientific knowledge that can benefit people, that can improve the lives of people, then we're doing something that is detrimental. It's not something neutral. So this is the first point, and I think you're absolutely right. I'm also happy that you mentioned your IPS because this is one of the organizations that are at the forefront of incorporating ethical considerations in the work they do. As you probably, I'm pretty sure you already know, the NeurIPS annual meeting has introduced a requirement for that all paper submissions include a statement of the potential broader impact of the work, including ethical aspects and future societal consequences. So this is definitely a positive development in this domain. On the issue of conflict of interest with sponsors, that's a very tricky one. And I think this is, again, one of the main areas of ethics in computing where we lag behind compared to other domains, such as the life sciences. Clinicians know well when they can receive funding from whom. We do not have similar standards for ourselves.
Cello.
Yes.
I'm sorry, but we're way over time. We have to go on because we have topic area meetings now. So we better wrap it up. Yeah.
Well,
thank you.
I'll just stop here. I'm happy to.
Yeah, I think we have to finish. Thank you for your contributions.
Sorry.
It's no problem. It's our job to stop you.
I mean, I think you can still carry on the discussion separately, but I think a lot of the other topic areas have organized meetings.
Yeah, they are already supposed to start their meetings now. So we unfortunately have to stop now.
So thank you.
Thank you all for your participation. I'm going to stop the live stream now and see you guys tomorrow for the next